Okay, we'll start in a couple of minutes. If someone online could confirm that they can hear me, then we will be good to go.
Yes, I can hear you.
Excellent, thank you. Fine. All right, let's get started. So, welcome to this training. It's training organized by the Flemish Supercomputing Center in collaboration with University Belgium. And you also perhaps recognize the Praise logo. So at some point this was a Praise training, and out of nostalgia, I like to keep the logo on. It's not that Praise doesn't exist anymore, but it morphed into something different than it used to be. And yeah, good old days, etc. Anyway, okay. What is going on with my pointer? That is weird. Okay, my pointer seems to be out of battery, which is rather annoying. Okay, then I need to move the slides manually. Let me meanwhile charge my pointer, and perhaps after the break I can actually use it. Okay. All right. So, hopefully the thing charges. Remark in the chat. Let's see. Yeah, that's true. But do you think it's out of battery? Was there a warning? I don't think it's yet out of battery, but let's see. I still have 55 minutes to go, so that should be fine. But rest assured, the power supply is plugged in and ready to be connected, so no worries there. Okay, so let's try to move this thing manually. So this QR code basically brings you to a small website. And of course, I'll put the URL in the chat because that's much more convenient for people online. Where does it bring you? Well, basically here. And that gives you some information about this training. It is a table of contents, the requirements, and so on, which is all not so very interesting. But the more interesting thing is that it has a link to a GitHub repository. This is the link here. And that brings you to the GitHub repository, which is this one. And that contains, on one hand, the slides, which is already useful, but on the other hand, also a directory with source code, all the code that has been used in order to develop this training, and of course, extra material for which I don't have time to delve into. So feel free to fork the repository, clone it, whatever. It's licensed very liberally, so feel free to use that. Okay. Yeah, I already thought that it wouldn't work while charging. Yeah, maybe. Yeah, but then I don't have enough USB ports. Okay, that's not going to work. Okay, so another QR code for our LinkedIn stream. So basically, it's a good idea to keep in touch with us on topics like training, on topics like HPC in general, in Flanders and elsewhere. So it's always a good idea to stay connected. All right, some practical things. Yeah, no problem. Some echo in the room. Some practical things, a bit of convention about the slides. So basically, if there is something happening on the command line, although I think in this presentation there's not that much, it will be rendered on a black background. And to remind you visually that it's a terminal thing, there is a $sign. So of course, don't type the $sign, it's just there as a visual reminder. Then I really don't think there's any IPython. So let's forget about that. So apart from that, in the slides themselves, inline code is rendered in monospaced font to make it stand out. And longer fragments of code are same font, gray background. For data files, same font, different color background, just to make it easily distinguishable. If you see gray, it's code. If you see yellowish or whatever that color is, then basically it means it's data. What you see from time to time is ellipses, which basically means not enough screen real estate in order to put all the code or all the data on the screen. For data, it's easy. It's just more of the same. For code, it might be something that's either explained on the previous slide or on the next slide, or it's obvious, or if all else fails, you find the code anyway in the repository. Okay, then apart from that, some two additional things. Basically, this is recorded. I'm not going to publish the recording, but if you want access to it, you can request access. Just send me an email and I send you the link. Bear in mind that this is quite a bit of video material, so it takes a while to process. With some luck, I can post the video of this session by this evening. And of course, the same for tomorrow's part, that will be posted by tomorrow evening, something like that. That's one practical thing. The other practical thing is that I like questions. So basically, if this is interactive, it's nice for me, and perhaps it's also more useful for you. So the people in the room have an easy time. They can just ask. The people online, please use the chat. If necessary, I can ask you to activate your microphone, but maybe it's good for everyone if we can make this interactive. Okay, so some general considerations about Python. I probably don't need to convince you that Python is used quite a lot in scientific computing, and apparently that is a good thing. And I would definitely support that view. However, out of the box, unfortunately, Python is pretty slow. It's never been a language that was designed for scientific computing in the first place, so for intensive calculations. And also by its nature, it is yeah, among the slower scripting languages. It ranks number 20, I think, according to in a ranking of scripting languages. So you're not even comparing it to true HPC languages such as C++, Fortran, or C. So even in its own category, it is rather slow. That is improving, let's be very clear about that. In each major release, strides are made. 3.13 was faster than 3.11, etc., then 3.12, etc., etc. So there are gains, but yeah, that's of the order of 50% at best. So that's not much of catching up with the faster alternatives. So that is just something to keep in mind, that yeah, it's just reality. However, of course, Python is a nice programming language to work in for several reasons. It is a very terse language. So basically that means with little code you can express quite a lot of intent. So that's a good thing. Python is also very close to English. So basically it's very natural to write a program in Python. So those are good things. Also, the development cycle is pretty short in the sense that you write code, you run, you fix, you run, you fix again, you run, etc., etc. There is no building involved, which basically speeds things up, speeds the development process up. So that means that Python is quite a good language for prototyping. If I quickly want to see whether an idea works, okay, I can just implement it in Python. That goes pretty fast. And if things work, then I can do several things, which we'll talk about today and tomorrow, in order to speed things up rather significantly. So that is definitely a good reason to use Python. And then, of course, there is a question, do you actually need performance? In the sense that if you have a script that runs an hour and you run that once every month, do you want to take the time to improve its performance so that it runs in 10 minutes? Good question. The answer to that lies in a small calculation. How much energy is used to run it during an hour versus to run it during 10 minutes? How much money is that? Literally money. Both in terms of energy and in terms of hardware. And how much will it cost you in order to improve the performance? It won't cost you anything. So in other words, how much money does it cost the taxpayer? Because that's the person who is paying your wages at the end of the day. So basically, that's always something you have to balance. How much effort, how much money, literally, are you going to spend on optimizing code versus the gain you are potentially getting? That's the consideration which should always be in the back of your mind, because otherwise it's quite possible that you spend a lot of taxpayers' money, maybe even without realizing it, to gain very little. Okay. So essentially, for a computationally intensive task, Python is not okay. Not really okay, but really not okay, essentially. And that's not a problem because there are many ways to get around that and to actually get very decent performance. And that is what this training is specifically about. For those of you who attended another training which I give, which is Scientific Python, you will recognize this slide. But I'm going to repeat it for the others anyway, because it's important to understand why we have these performance issues with Python and why out of the box, again, it's not necessarily your best choice to use vanilla Python. So this is a small fragment of code, and everyone will recognize that. It is essentially just a matrix-matrix multiplication. That's the second function. And the first function just initializes the matrix. So not particularly exciting. So the question is, how long does that take? This is a very trivial implementation, so shouldn't be too bad. And let's run that on 500 by 500 matrices. And then you see that when you time this, you get 1/10 of a second for the initialization of the matrix, which may or may not be fine. And you get 32 seconds for the matrix multiplication. Okay, so question, according to your gut feeling, what do you think? Is that fast? Is that slow? Is that acceptable? What's your opinion about it? It seems slow. It seems very, very slow. Maybe we can try to quantify this, and that's always a good exercise to do, because that gives you, let's say, at least a ballpark number of what you might expect. So in order to do that, we need to look at our code and what it is essentially doing. It's 3 nested for loops. As such, there's nothing wrong with that, but that means that what we need to do is essentially look at the body of the inner loop, because that's where the heavy lifting is going to happen. Outside of that inner loop, there is just a single assignment, so yeah, that is peanuts. We don't care. So we're interested in the inner loop. That's the thing that happens. Okay, so what happens there? That's a multiplication and an addition. That's it. Okay, so if you know a little bit about how CPUs work, then basically you know that if you do many operations like this, so many multiplications, many additions, essentially you can do one per cycle. So each elementary operation of a CPU, each machine instruction happens in a cycle, and it just takes a single cycle, single instruction, not quite true, to do this multiplication and this addition. This is a simplification. But anyway, bear with me. So basically that means each cycle I can do one multiplication and one addition. And on modern hardware, in fact, I can do this operation in one cycle, because there is something called a fused multiply add. So essentially this is just a single cycle. Okay, now that's great if you know how many cycles you do, but okay, that's easy, because that's what tells you how many cycles there are per unit of time is the clock frequency of your CPU. So that's something like 2 gigahertz. So 2 billion cycles per second. Okay. So essentially that means that you can do 2 billion additions and 2 billion multiplications like this per second. Okay. Of course, these are ballpark numbers. Your hardware may run a bit faster, its clock frequency may be a bit larger, etc., etc. There are a number of things which I don't take into account, but I just want ballpark numbers here. Okay, so I can do 2 billion of these operations per second. That's great. Now, how many operations should I do? Well, basically, if I count this as 1, I can also count it as 2, depending on which hardware, but again, no one cares. So basically, I have the 3 nested for loops. Each for loop has 500 iterations, so that's 500 to the power 3. That's 125 million operations that need to be done in order to compute this. Okay, let's say this is not optimized. Let's say it's 250 million because the fused multiply add is not happening. So, okay, 200 million. So I should end up with something around 1/10 of a second, give or take. Again, ballpark numbers, I don't care. So from this back of the envelope computation, it's very clear that this 32 seconds is way too slow. That's a few orders of magnitude off. Okay. So this is a kind of reasoning you can always make. You look at your code, you see, you count the number of operations essentially, and you compare how many you can do per unit of time, and you're good to go. You can also take another approach. You can say, okay, this is very simple, so it's very easy to implement this, for instance, in C. And then you see that indeed the matrix-matrix multiplication happens in half a second. So we're getting significantly closer to that back of the envelope number that we just computed. Okay, great. So clearly this demonstrates that this computation can be done a lot faster than in 32 seconds. Great. Let's do that in Fortran. Again, just a naive approach. And you see that we go down to 1/10 of a second. A little bit more, whatever. So basically, you see that we get very close to our very rough end. Okay, that's nice. So basically, that shows that indeed, if I just use Python out of the box, I might have a performance issue. Now, okay, great. Now we see that that happens. This is an illustration that that happens, but we don't have an explanation yet. So why is this happening? Why is this so slow as compared to C and Fortran and whatever you may choose? Why would that be?
I don't know perfectly, but from what I remember, Python, the way it stores its arrays is not really structured. So one is that it's not a it's a list, so it can vary in data type, and the locations in which it stores its memory is not ordered. It can be anywhere, and so there's quite some latency in fetching data from the various memory locations to actually perform the operation and then manipulate the data.
So indeed, you have raised two very pertinent points. One of them is, let me rephrase, one of them is indeed that I have been deceiving you. I have been calling this a matrix. Okay, now if you think of a mathematical matrix, then of course what you have in mind is some mathematical structure with elements that all have the same types. All double precision numbers or single precision numbers or integers, I don't care what it is, but at any rate, the elements of the matrix all have the same type. Okay, that's one thing. The other thing is you think of it as a sort of monolithic, contiguous data stored contiguously in memory. So those are the two things you spontaneously think about when you hear the word matrix. Okay, great. Except that, of course, this is not a matrix in that sense. I have encoded my matrix as a list of lists. So that's exactly what you said. It's a list of lists. And the other point is, which you also raised, a list in Python can contain anything. It need not to be homogeneous in type. The first element can be a float, the second element can be a set, the third element can be a string, and no one cares. Yeah, you care, because basically that's what's killing your performance, in part. I come back to your second argument in a minute, but let's have a look at, indeed, this inner expression again. So what am I doing? I've got an object A, okay, and I do apply a square bracket operator. Okay, question number one, can I do that? Answer, yes, because A happens to be a list. Okay, so that's check number one. Check number two, I'm indexing, because that's the square bracket operator thing, with I. Okay, can I do that? Yes, because I happens to be an integer. Great. Then I need to check whether I is within bounds. So is I less than the length of my list? And is it larger than minus larger than or equal to minus the length of my list, because those are the valid indices of this list. Again, the answer is hopefully yes. It happens to be yes, but okay, great. So then I have AI. Now AI, I'm going to apply the indexing operator on. Again, the second pair of square brackets. That's great. So can I do that? Yes, because AI happens to be a list, because my quote-unquote matrix is indeed a list of lists. So yeah, I can apply that second indexing operation as well. But then I need to check K. You already know the drill. Is it the right type? Is it in the right range? Blah, blah, blah. Okay. Then I need to do the same thing for B, which we just did for A. Then we have to see whether the multiplication operator can be applied to AIK, BKJ. Yeah, it happens to work because the float's in there. Great. Then I need to do the same thing with C, the whole indexing thing, and then I need to verify that I can actually add the value of the product to Cij. Okay, all of that works because those are floats, blah, 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 list of lists, etc., etc. But I'm checking quite a lot of stuff here. And that's where your performance goes, in most part, because of all this type checking. And that, of course, is something that you can't really avoid with Python, because a list indeed can contain anything. So each element of the list has to be checked individually. So that's a problem. And that's indeed why you get this abysmal performance. You also raise another point, and that is how data is stored in memory. And I already said, well, okay, what you assume is that this data for this matrix is going to be stored contiguously in memory. So the first element next with the second element, the third element, and so on, up to the end of your array. For lists of lists, that is not the case necessarily. Part of it will be stored contiguously, but definitely not everything. And certainly if you have a list of lists, that data goes somewhere in memory. You don't know where, and unfortunately, fetching non-contiguous data is slower than fetching contiguous data. It's not going to be too bad. Let me reassure you, it's not that bad, essentially. As long as I go, in this case, row by row, it's not horrible. If I would go column by column, this would get interesting. And by the way, I do go column by column for B. For A, I go row by row. For B, I go column by column. Sorry, vice versa. For B, I go row by row. For A, I go column by column. So yeah, this is not going to be very performant for the reasons which you mentioned. Okay, so what to do? Well, basically, use a library which implements something better than what you do by hand. And in this case, it's easy. You can just use NumPy. Okay, so basically, NumPy gives you quite a number of things. It gives you dense matrices. It gives you dense matrix operations like matrix-matrix multiplication. It gives you fast Fourier transform. It gives you some linear algebra. It gives you statistics, mathematical functions on arrays, etc., etc. So it will give you all that. And out of the box, you will get a very reasonable performance on condition that NumPy under the hood is using the proper library. So basically, a matrix-matrix operation can be implemented using a library, a BLAS library, basic linear algebra subroutines, and there are several implementations of that. And NumPy under the hood is going to use one of these. Which one it uses depends on how you install things. So essentially, if you, for instance, use a package manager such as Conda, Mamba, or Friends, then it's useful to check once you install NumPy what the BLAS library is, because there's several options. For instance, it could be OpenBLAS, then you're good. It could be Intel MKL, then you're good. It could be NetBLAS, in that case, you're not good. It will work, it will be very slow, because NetBLAS is a BLAS implementation, but it is a reference implementation. So basically it's there in order to check correctness of other implementations, not full performance. So it's good practice to check that, because if you use NetBLAS, you will see a marked, yeah, okay, your code would run significantly slower than with a proper BLAS implementation. Okay, there's also SciPy, which gives you, for instance, sparse matrices, etc., linear algebra, and so on. So basically, that would help a lot for certain other operations. And again, SciPy, under the hood, is going to use NumPy, so is going to use that same BLAS library. It's also going to use LAPACK, which again is using BLAS under the hood. So basically everything is good once you have a good BLAS implementation. And that's performance which you get for free. So that's something to take into account and to make sure that you have proper implementation ready. Okay. So basically, the important thing here is don't reinvent the wheel unless you have a very excellent reason for that. Don't code your own matrix multiplication, because most likely there is a library that does it significantly faster than you do, unless that's your area of research and you want to improve the performance of matrix multiplication algorithms. Anyway, if you do that in NumPy, things get really, really simple. And as you can see, we actually get an execution time which is lower than Fortran. Fortran was 0.11 seconds. Now we are down to 0.077. So significantly lower. Okay, that's great. And the code is significantly simpler because we don't need a function anymore. We can just use the add operator to do the matrix multiplication, etc., etc. Okay, so essentially that means not using the correct libraries is going to slow you down by, in this particular case, for this benchmark, a factor of 415, which I would say is very, very significant. Of course, at the end of the day, Fortran in combination with the same BLAS library is going to do better, but not by that much. As you can see, there is a 10% performance gain if you code this in pure Fortran, doing the same BLAS thing, etc., etc. But okay, ballpark numbers are more or less the same. Okay, so this is performance for free. There's no reason not to do this. And this is a recurring theme. So what we're going to do is we're going to build up in the sense that we'll start with things that are free, then things that are cheap in terms of effort on your part, and then let's say a bit more expensive in effort on your part, and you will see performance increases depending on how much effort you're willing to spend or able to spend. So that's a bit the recurring theme of the whole training here. Oh, well, okay, not the whole training, but a large part of it at least. Okay, so this gives you some idea of performance, and also I think the back of the envelope thing is quite useful. If you've never done it, then basically this is a good habit to get into so that you start to estimate how much you expect with respect to performance. Okay, so this was easy, just use NumPy. Okay, a little bit more effort, but again, very, very cheap, is use the right starting point. So, of course, most of you will be familiar with Conda, Mamba in order to get your environments. And that's, of course, quite a good approach. But it depends a little bit on what your baseline is. And, of course, you can just use anything as a baseline, but it might be a very good idea to actually use the Intel's Python distribution as a baseline. So that might surprise you a little bit, if you're not aware of it, but actually Intel makes a Python distribution, and that's part of its One API framework, and it is available certainly for researchers, and nowadays also for industry at no cost. So that's actually quite nice. There is a standalone installer, so you can download that. You can do that using containers, but there is also a Conda channel. So basically, it's quite possible to simply create your own environment based on the Intel channel. And then, of course, the important stuff, everything that does the heavy lifting, comes from that channel. What is the advantage? Basically, Intel has spent quite a bit of time in order to optimize libraries for its CPUs, so basically for performance. And so, for instance, things they have looked at are NumPy and SciPy, but also things like sklearn and other packages. So it also means that under the hood, you will actually get the mod kernel library, so Intel MKL, runtime libraries for matrix computations, for linear algebra, and so on. So that gives you, out of the box, quite a bit of a performance boost. Is this major? No, not necessarily. It depends on what you're doing, but it may give you 50%, a factor of 2, depending on what you're doing. So again, a very easy game. Just start out of the Intel channel and use stuff which is there. The Python version which they support is not the very latest one. So typically there are like 2 versions behind. By now, I would expect they have Python 3.12 already, while we're actually at Python 3.14 in the rest of the world. Does that matter? Maybe, probably not. So probably you're good using 3.12 or even 3.11. Okay, so that's again very easy gains, low hanging fruit. As you can see, there is also thread scheduling with TBB. We will be talking a little bit about MPI. So Intel has a very good MPI library, and that is provided as well. So basically, under the hood, they have done quite a bit of optimization, which you can benefit from, essentially for free in a way. Okay. What you can also do, but which is slightly more adventurous, is using an alternative interpreter. So everyone and his dog is using CPython, which is basically the default Python interpreter implemented in C and giving you the performance that you get out of the box, which is, as we already have seen, not that great. Are there alternatives? Yes, there's actually a thing called PyPy. Notice the double Y rather than the IY. So don't confuse PyPy and PyPy. Sorry for the feeble pun. So basically, this is an alternative interpreter. So normally, it will outperform the standard Python interpreter because it's a just-in-time interpreter. Python, the standard interpreter, is also adding those features, but PyPy is ahead. So basically, you get typically better performance out of the box. So one of the things that implies, of course, is that this only helps when your code runs for a significant time, because you have overhead first doing that ahead of just-in-time compilation. So basically, that means you need to make up for it in terms of execution time. Now, of course, many things in science are iterative. So basically, that means that once your loop body is compiled, you start gaining immediately. And you have many iterations, so yeah. So that's pretty cheap and sort of interesting in that respect. So, of course, The only thing which will be sped up is Python code. All the rest is not going to speed up. Wait, what's all the rest? Well, what I didn't tell you is that libraries such as NumPy, SciPy, and so on, that's not Python. Well, yeah, there is a Python layer around that, but essentially what is under the hood is C or C++. So, of course, if you run such calls to such libraries, then of course that is no longer Python. That is machine code that's directly being executed. So obviously PyPy can't have the potential to speed that up. It can only speed up Python, pure Python. That's it. So if your application is NumPy heavy, let's put it that way, then you're not going to gain that much. So for some applications, it can be quite convenient. It will also save memory because it does things in a more intelligent way than the Python interpreter does. So basically, yeah, let's forget about Python 2 compatibility. So essentially, also, it lags behind a little bit. So last time at the presentation, I forgot to check now, but basically, PyPy is also a couple of Python versions behind. I expect by now it's Python 3.11, which they support. So that's something to keep in mind. Also, something to keep in mind, which is also non-trivial, is not all Python packages are supported. So before deciding to switch to PyPy, have a look at this list of packages, whether it makes sense or not. Apart from that, of course, it's very easy. Rather than executing your script with Python script name, you execute it with PyPy script name. That's all you need to do. The rest is for free. So it can be worth to try, but again, remember all the caveats. That's unfortunately something you have to take into account. Okay, so actually, if you're lucky, basically, if your code is really pure Python and so on, you can gain a factor of 10, which is rather nice for not having to do any effort. Okay. It doesn't cover all use cases, but whatever. So NumPy is a C++ C library. I think it's C, not C++. I'm not sure. Never looked into the source code myself, but basically it's not Python. So what is happening? Well, essentially you do a function call of NumPy. So basically you are at the Python level, let's say. You dive into the C level, so things go fast. And then after that function call, you're going to resurface to the Python level, things go slow again, until the next NumPy call, you dive to a higher performance, etc., etc. So that's basically the mode of operation. You continuously switch between contexts, slow Python versus fast NumPy. Okay, so that's fine, typically, unless you have chained operations. What do I mean by changed operations? Well, very simple example. There will be one on the slide. So basically, no, there isn't one on the slide apparently. Okay. So basically, don't have a slide on this. This is annoying. Yeah, here it is. I'm going to start with this slide because then it's immediately clear what I mean, and I can more easily explain this. I would like just simply a numerical example. Yeah, so I would like to start with this one to really reorder the slide at some point. So basically, what do we have here? Well, it's a simple operation. We have two large two-dimensional arrays, or three large-dimensional arrays. So A, B, C are all two-dimensional arrays, same shape, and we do an operation to them. basically we multiply A by 3, we multiply B by C to the power 3. Okay, so if I were just to write this as a Python expression, then of course it would be quite simple. I would write something like D equals 3A plus B times C to the power 3. Okay, but yeah, these operations will be done one by one, in the sense that the first thing that happens is that A is multiplied by 3. That gives me a temporary two-dimensional array, same shape as A, with that result in it. And that we are happy because that's going to happen in NumPy. Okay, then of course we have C to the power 3. Again, easy. We get a temporary array with that result. But it happens in NumPy, so it will be pretty fast. Okay, so we've got, by the way, now 2 temporary arrays, which I may or may not be happy about. And then I have to multiply B and C to the power 3. Again, I get some temporary array with that result in. And again, I'm happy because that happens in NumPy, and that's going to be fast. And finally, I'm left with 2 temporary arrays, which I need to add. Again, by NumPy, easy, fast, and so on. But each time, we dove into NumPy and we resurfaced to Python again. For 3 times A, then for C to the power 3, then for B times C to the power 3, then for our addition. Each time the same thing happened. But if you look at this, then this could be much more conveniently done without temporary arrays. Because at the end of the day, all of this is element-wise operations. I multiply each element of A by 3. I raise each element of C to the power 3, etc., etc. So essentially, I could write Dij, so a component of D, as 3Aij plus Bij times Cij raised to the power 3. Okay, there's a multiplication somewhere rather than an addition, but you see where this is going. So I could do that element-wise and immediately compute the final result in D without intermediate arrays. But since I'm using Python, since I have these function calls, temporary arrays will be there. So that takes time, that takes memory, which is sort of unpleasant. Can we avoid this? Well, there is a very small library which is called numExpression, so numexpr, actually, and that will do that type of thing for you. So basically, rather than writing D equals 3 times A plus B C to, times C to the power 3, what you write is this thing here, NE for numExpression, dot evaluate, and to represent your arithmetic operation as a string. And that's going to speed up things rather considerably. It's a factor of 22 for this operation. On a single core, we'll later talk about multiple cores and so on. But basically, this is a pretty huge speed up, which you get almost for free. So you import numExpress NE, and you just do the NE evaluate. And that gives you, in this case, a significant speed up. Okay. So it also has, you can also do that for a where expression. So basically, a where expression takes a Boolean expression as its first argument and then 2 values. And depending on the result of the Boolean expression, whether it's true or false, it's going to be either the first or the second value, respectively, which is assigned. And that again is, of course, going to create a number of temporary arrays. Because this Boolean expression, A is again a multi-dimensional array, so for instance, a 2-dimensional array with a lot of elements. So the first thing we need to create, if we do this in pure Python, so the np where something something, is indeed creating a temporary array with this Boolean mask, essentially. And of course, again, that's not really required, because this can be done element-wise. This where expression, this Boolean expression, is an element-wise expression. So it just compares each element of K, in this case, to the value 1/2, whether it's large or not. That's all it does. So again, I can just do this element-wise, no temporaries involved. And that's exactly what, in this case, the NE evaluate is going to do. It's going to evaluate that where expression in that way. And you get not that much, 10%, so way less than the factor of 22 for the arithmetic expression, but still, if you do this quite a lot, it might be worth your while. Okay, so this is almost for free. Yes, your code starts to change. You have an extra dependency num expression, that's one thing, and your code relies on the existence of that library or on the fact that the library is available. So something happens. Let me go back to the previous slide if I manage. Okay, something is. Okay, that's better. Right. So let me get back to this slide. So basically, it can compile and evaluate NumPy expressions. So we saw that it can speed up computations. It conserves memory because in many operations these temporary arrays are uninteresting, not necessary. And basically under the hood, it can also use some Python libraries, like for instance, a library I didn't mention, Intel VML. So those are vector matrix operations on small matrices. So that is optimized and is mainly for image processing, but of course any mathematics that requires that can benefit from it. And that also gives you automatic multi-threading, so basically using multiple cores if they're available on the system. Now, of course, this is not for free in the sense that there are a number of restrictions. One restriction is that it deals only with element-wise operations. And that was indeed the case for our where. That was indeed the case for our matrix arithmetic. So what it's not going to do, of course, and will refuse to do, is to evaluate, to speed up a dot product, so or a matrix-matrix product, because that's not element-wise, so that is not going to happen. It can do quite a lot of trigonometric functions, so that would work as well. Of course, again, you would have to verify which are supported. Logarithms, exponentials, square root, etc., etc. It will all happily do that. And there are also some accumulation functions, such as sum and product. So to aggregate data in an array, that can also be part of num expression evaluation. Okay. All right. This I already showed you. So basically, there is documentation about num expression, and of course, it would be a good idea to check that when you decide to use it. Okay, so we've talked about almost free speedups, but is it worth it? Because it's entirely possible that I spend a little bit of effort, or quite a lot of effort, on optimizing part of my code that is in fact not really the bottleneck. And it requires quite a bit of experience to just, with, let's say, unknown code, to know where your bottlenecks are. And starting to optimize, spending time, essentially, before you know what your real performance bottleneck is maybe not your best investment of time. So that is actually where profiling is going to help you. So don't optimize blindly. The worst thing you can do is take your code, look at it and say, okay, this I'm going to optimize. You may be right or not. If you're not right, you spend quite a lot of time for very little gain. So why take chances? Why not just use tools which are readily available and which give you actual numerical information about how much time things take? So there are several ways to profile, to benchmark. One of them you might be familiar with, and that's micro-benchmarking. So essentially that is using timing information for a particular function, for a particular expression. In Jupyter Notebooks, that would be your time or time magic, or a similar library, which is in the Python standard library, in order to time small fragments of code. That is, of course, useful. Don't get me wrong, it's part of your toolbox. But that is not typically the starting point. Why? Because you will be tempted to optimize at that stage. You time something, you think, okay, yeah, this is not going so fast, let me try something else, let me re-implement this and this and this. Oh yeah, now it's 10 times faster. Yeah, that's great. But that's micro optimizations and potentially premature optimization. Because it might be that you just spent a happy afternoon or frustrating afternoon, depending on your perspective on programming, optimizing a function or an expression that only takes 1% of your total CPU time of your application. That's great. That means that you sped up 1% of the execution time by a factor of 10. Okay. So essentially that means if your original application took 100 seconds to execute, after an afternoon's work, it will take 99.1 seconds. Might be slightly disappointing for an afternoon's work. So that's the risk if you concentrate on individual expressions without taking into account the bigger picture. And that's what is referred to as premature optimization. And for Python programmers, and by the way, for Julia programmers, same thing, you are tempted to do that because it's very easy to do these kind of timings. So it's tempting. So I would say don't do that because it might be a waste of time. So profile first with a proper profiling tool. That's a tool that gives you an overview of where your execution time is actually being spent. Which functions are your performance bottlenecks? Not necessarily performance bottlenecks, but which functions are you spend the most time in, execution spends the most time in. Okay, so it's a bit more complicated, but then again, it's not as if it's rocket science. So basically, it's an excellent tool to get in your toolbox. And of course, I'm saying, okay, profiling is very useful, but I'm not saying that micro benchmarking is not useful. On the contrary, they go hand in hand. But start by profiling and then, if necessary, micro benchmark in order to improve performance. So, to time individual functions, you can, for instance, on the in the Python interpreter, or in IPython, or in Jupyter Notebooks, and so on, you can use the time magic. So basically, as you can see, there is the magic thing, time it. It's magic because there is a percentage sign in front of it, and yeah, that's what it's called. It's magic, can't help it. So basically what it will do is it will execute that expression which follows it multiple times. It's going to time each execution, and it's going to compute statistics about the whole thing. So quite useful, and also something that you should be aware of. So basically, why is it computing that statistics that execution time multiple times. So why is it executing that function multiple times? Basically because it might be that, for instance, your first execution is significantly slower than subsequent executions. That might sound strange, but basically the CPU frequency of your system is not necessarily fixed. It may change depending on load. So for instance, if my laptop is just showing this PowerPoint presentation, it's going to run at a frequency of probably 2.1 gigahertz or something like that. However, if I give it something to do, it will ramp up. It will ramp up to, at most, 4.5 gigahertz for this particular laptop. But basically, things will speed up pretty impressively by a factor of 2. Of course, that takes a while. It also takes a while for the CPU to decide, am I going to ramp up or not? Not that the decision process by itself takes much time, but there is some leeway here, because if there is just a short sudden spike, yeah, you're not going to increase the clock frequency. So basically, that only happens after a while. So that is one reason why this is executed multiple times. There are also other reasons, which I'm not going into right now. I'll mention them later on. But if you're benchmarking, and that goes for micro benchmarking, but actually also for true benchmarking, always compute an average. Don't base your benchmark on a single run. Always have several runs and do the statistics. Okay, so this is, of course, quite useful. Okay, so this is micro benchmarking, and you can also do that on the command line. I would not recommend this because you are evaluating an expression. Python is whitespace sensitive, so to get this right is not always obvious. But yeah, you can do that if you want to. I never do, but okay. All right, so this was easy. How difficult is profiling? Because I told you, okay, it's actually very useful. It's a bit harder. How much harder is it? Well, not that much. Because the thing I do is I execute my script, and I'm using the cprofile module. So the -m cprofile means run this, this script using the cprofile. So that's part of your Python standard library. It comes with every Python distribution. So that's easy. You don't need to install anything. It just works. And then the thing you say is, okay, I want to sort results by time. So what I will get is a list of functions which are called in my application, and the time spent in that function, the number of times it's called, and the time in total, and the time per call. So those are metrics which are computed for each function in my application. So this gives me a true view of where my execution time is going. Basically, if you look at the cumulative time, you see that in fact this function here, which is the primes function somewhere, is taking the majority of the time. So it's taking the lion's share of the execution. Then there is a function which is called many times, and that's the list function. Sorry, the append method of list. So this is all interesting information. So not only the times, but also sometimes just the number of times the function is called, because that might be sometimes unexpected. In this case, an append for a list that is called multiple times. Okay, that's not that weird. So it's kind of expected, and the cumulative time is very low. But that basically means that if I want to optimize this application, this function I should look into. And that's quite clear. I immediately know where to look for. Yeah.
What's the difference between total time and cumulative time, and the difference between the two per call codes?
Yeah. Basically, now I have to think for a second. So there is the time spent in the function itself, and then the time spent in the function and the functions it calls. So those two are taken apart. It's very easy to distinguish when the numbers are different. Yeah. Because of course one of them will be larger if it includes also the time spent in functions that are being called by the function on that line, then of course the number is larger. Yeah. Here, to be honest, I can't see it. Yeah, I can see it. So basically here per call we have slightly more in this function. So this is including all the functions that are called in primes, and this is the time spent in primes itself. Okay. So it's interesting to have that, because basically it also tells you if it tells me immediately something. That is, if the majority of my time is spent in the function itself, then that's where I should look, for sure. If a lot of time is spent in functions that are called by this function, then I need to start checking which functions are called, etc., why they are called, and so on, and whether it makes sense or not. It may make sense. I mean, it's perfectly possible that it makes a lot of sense. But, so that's the distinction. And yeah, the cumulative time versus total time, yeah, it's a name, and it's not that informative because I have to sit down and think what it means exactly. But that's the two quantities which are relevant. Okay. So don't start optimizing before you actually know which functions are your bottleneck. Okay. So this is textual information, which is okay, but which may or may not be easy to interpret. So you can also visualize it. And there is very nice module to do that. So what you would do then is, rather than have that profile being printed to standard out, you save it into a file. That's just with the -o flag followed by the file name, and then you can analyze that profile later on with different tools, for instance with SnakeFizz. So that's a separate Python package, and that allows you to visualize such a profile in two ways. This is an onion representation. You can also have an what's it called? When you have ice and it drips from something, and you get these stalactites of ice. What's it called in English? Can't remember the name. But anyway, it's different representations of the same thing. That's all it does. So basically, it's a call stack, which is represented here. So you know that if a function calls another function, you get a new stack on the frame. If that function calls another function, etc., etc. So this representation is exactly this call stack. So that's the main function here, and that calls this function in purple, plus the one in orange, the one in blue, and whatever other colors are here, marginally small. And that function in turn, this purple one, again calls another function, and no more than one. So basically this is your call stack. The interpreter itself, your main script, then a function which is called, and that function calls other functions, etc., etc. And that gives you an immediate graphical representation of where your time is going. Because of course what I should look at is this purple function here. That's my culprit, well, my culprit. That's where the action is. So that's a very easy representation. Icicles, that's the thing I was looking for. The word I was looking for the other representation. Which one you prefer? Yeah, that's up to you. I like this onion view, but it's personal. Yeah. So basically, what you get from SnakeMake is a web page. It will just open your browser, show this in a web page. You can hover, and then you get the function name, which is in that particular slice of that diagram. So it's very convenient. You can also filter a little bit here. Basically, this is the mode. So this is sunburst, which I call onion representation. You can choose icicles. You can limit the depth. So how large, how high can your call stack be, etc. You have a certain cutoff where things are not shown anymore, etc., etc. So you can tune what you see a little bit in function of what you want to see. Okay, so I would say pretty straightforward. And here, of course, you get numbers, etc. So that makes it quantitative. Okay, so that's great. And that gives you quite some information, but we're not really there yet, because that is, of course, information at the level of functions. Now, what if you're interested in information within functions? So in many tools don't really support that. So if you wanted to know that for certain applications, you would have to kind of rewrite them a little bit and wrap things in functions in order to figure that out. But for Python, you can actually use a different profiling tool, which is called a line profiler. So that's yet another Python package which you can install. And as you can see, I can run code prof, which is basically that tool, on my script, and I again get some output. So basically, I get line by line similar information. So I get the number of hits of that line. So in this case, each line is just executed once. But of course, if I'm in a for loop, then of course that will be, the count will be much higher. The time which is spent, the time spent per hit, which is of course identical if this is 1, so this is just an average, and then the percentage of the time. And so basically this gives me, at line per line level, information about my performance. And as you can see, actually nothing much of interest is happening here, except in this signal line. So if I would like to speed up this application, and this would be a relevant part of my application, then I would have to look at this line and try to do something that is has better performance. Okay, this is expensive. This is really expensive. So the profiler, the C profiler, which I showed you in the previous slide, is going to increase execution time by 50%, by a factor of 2 approximately. So it's not cheap, but this is expensive. I mean, we are talking a factor of 10 in execution time or more. Okay, so this is a second level tool. First, you use something which is cheap with respect to execution time, like C profile. Then you know the functions of interest, and then you can profile those functions using the line profiler. And as you have probably already spotted, there is a decorator here at the function definition. So that basically means the only thing that the line profiler is looking at is this particular function in my code base. So I can add as many decorators as I want, but if I do that judiciously, of course, then my execution times might still be reasonable. So that's why I would call this a second step after a C profile. C profile tells you the function, line profile will tell you the lines in hot functions, in functions that are potential performance bottlenecks. Okay. So this already tells you something which is interesting, namely that this array function and the way it is being used is actually quite slow. So this is not a very good way to represent data in Python. The main reason is the fact that this is a rather large array, and that, well, 1,000 elements is not that large, but that you need a list in order to initialize that array. So you first need to construct a list, and then out of that you create an array, so that's a little annoying. And that's the reason why this is not a good performer. Okay. So what's your optimization workflow? I've already hinted at it. So basically, you first profile with cprofile. That gives you the functions you're looking for. Then you can potentially use line profiler in order to figure out which lines are giving your performance bottlenecks. But again, remember, line profile, that's a lot of overhead. So use it sparingly, and especially use it judiciously. So basically, this is essentially a cycle. Then once you have identified lines of interest, then you can start using tools like TimeIt, so micro benchmarking, in order to try and find something which is faster. So for instance, the thing I would try for this particular example is see how long it takes to create an array of 1,000 elements using Python's standard array function and compare that with NumPy, for instance. And for this, I would just use TimeIt. And then if I would be convinced that NumPy is faster, I'd rewrite my code to use that rather than array. And then, of course, I would profile again and see whether indeed my hypothesis is correct, that this solves one of the performance bottlenecks in this code. So that's basically the idea. But that also means now we rewrite our code. So who says that after rewriting it, we still get the same results, that our code is still correct? So that's where unit testing comes in, because that ensures that you can run your code, you can change your code, you can test your code. If all your tests still succeed, at least you haven't broken something while rewriting for performance. So if you're doing performance optimization, it's really a good idea to have testing in place. Unit testing in Python you can do with PyTest. The other framework, I would say PyTest is the dominant one. So this really gives you confidence that you can rewrite your code and that you have a level of assurance, let's mildly put it that way, that after rewriting it, it is still doing the same thing. Not necessarily correct, because it might be broken in the first place, but at least you didn't introduce extra defects. Okay, so that's quite important. And then, of course, what helps you as well, pretty obviously, is version control, because yeah, if you try something, you introduce NumPy, with micro benchmarking it seems fine, but it, at the end of the day, creates another bottleneck, and you want to go back, yeah, that's where version control comes in. You just restore the previous version and you're done. So easy. So this is where software engineering best practices get kind of important. Okay. By the way, it's not in the slides. I always forget to add it. I'm going to make a note now. Maybe this time I don't forget to add it. There is another tool which is useful, and that's the memory profiler. So one of the things that also takes quite a bit of time, or that may be a performance thing, or that you might be interested in just for different reasons, is how much data do your data structures use? Because sometimes you might be surprised about data usage of certain data. For instance, if I use a list of lists to represent the matrix, that is going memory-wise to be less efficient than my NumPy array. Memory-wise, I mean with respect to memory consumption. There will be overhead for the list. So how much is it? I don't know. But that's something that you can figure out with the memory profiler if you're interested. The memory profiler works very similar to the line profiler. So it will also annotate your code with the memory usage of certain lines. So that is interesting information as well. So the summary of this section is essentially this slide. If you don't profile, go directly to jail, you don't get any money. You might recognize this from Monopoly. So basically, yeah. As a German colleague used to say, you really have to use a profiler. It's the law. Might be in Germany, I don't think so, but I always like the joke. So basically, it's definitely good practice to profile. Okay, any questions at this point? No questions online, no questions in the room. Okay. All right, let's speed up things. Well, let's speed up our code at least. One of the first ways to speed up stuff is Numba. And it's actually a very nice project. I really like it. I'll talk about it today in the context of CPUs. I'll also talk about it on Thursday in the context of GPUs, because you can do both. Meanwhile, my presentation thingy is charged, I hope. So if it wasn't broken and only out of battery, then yeah, it works. Great. Life is back to normal. Okay, so basically, what is Numba? Well, it's a neat thing. The only thing you need to do is decorate your functions. That's easy, and then you get a speed up. Okay, that's magic. So how does it work? Well, what is going to happen under the hood is that your Python function is going to be translated into C++. That C++ is going to be compiled, and it's going to be that compiled code which is run. And of course, that potentially gives you a rather big speed up. Remember the example on the first slide. So basically my matrix-matrix multiplication, if I do it in Python, it takes 32 seconds. If I would use Numba, I know that I can go down to half a second, because that was the time which my C implementation took. So if Numba is worth its salt, it should even do a little bit better. But at least I know that I can go down by a factor of, what is it, 60, which is quite good. So that's the potential. Is that realized? We'll see. Okay. So the nice thing is that this code generation under the hood and this compilation and so on, it's all transparent to you as a application user. So basically it happens and you don't even need to realize it's there. So that's a good thing. If you really use it in a very simple way, in a very naive way, you get quite decent performance. If you want to get better, you need to help the compiler a little bit. And it's not rocket science, so we'll see how to do that. So it will also happily generate CUDA or HIP code for you if you want. It works both on NVIDIA and AMD GPUs. But again, I'm not going to talk about that today. So a question which is always the case, or which you should always pose, is it worth the investment? So I've already asked you, okay, is it worth it for the expression? The investment was very little. You could potentially gain a little bit with where. You could gain something substantial with the arithmetic expression of arrays. So it's always the same trade-off. What's the effort you put in as a developer versus what do I get back, or what do you get back with respect to performance improvements? So that's the running question for each framework. So let's take a few examples, and let's start with a very simple one. We want the first n prime numbers. So not the prime numbers up to a certain value, but the first n. That's the idea. Okay, and I want the result to be a list at the end of the day. Okay, so let's not look at the code, let's look at the timings first, because that gives us an idea about whether it's worth bothering or not. Okay, so there are two versions of this code, primes p and primes n. So primes p is the vanilla Python implementation. The n version is the one generated by Numba, essentially. Okay, and then, as you can see, both are run using timeit, and as you can see, we get what is it? How to read 5 milliseconds for the Numba version and 300 milliseconds for the Python version. That's not bad. That's a factor of 60. Okay. Okay, 54. If I could read it, then probably I could have done a better estimation. But basically, this seems worth it. If I can get a speed up of a factor of 50, that's rather interesting. That's the most we had up to this point. So this seems promising. Now, of course, the flip side of that question is how much effort do I need to spend in order to get this 54 speed up? If I have to sit down for 3 months to recode my project, then of course it might not be worth it. So let's have a look at the code. Well, this is the Python implementation, the pure Python implementation. And as you can see, there's an array generated of 1,000 elements. It's immediately initialized to 0. That's just a NumPy call. And then we do some iterations here in order to compute the numbers, and they're stored into a result array. Nothing much special. I only store a number when it's a prime number. I detect whether it's a prime number with this pretty naive method, but okay, bear with me. You can do this a lot smarter. I don't bother. No one cares in this case. It's just a benchmark. Okay, so pretty straightforward code, a bit convoluted, but yeah, nothing out of the ordinary, I'd say. It's just standard code. So this is the Numba version, and yeah, what has changed is marked in red. So from Numba import JIT, my function decorated with JIT, that's the entirety of the changes I make. That's pretty cheap. I just add an import statement and a decorator, and I get a factor of 50 performance increase. That's kind of neat, I'd say. Okay, great. So that's quite interesting, because note that that implies that Numba can deal with NumPy arrays, which is already quite interesting if you're into scientific computing. It knows what it is, it knows how to do something sensible with it. Okay, that's cute. So this was really trivial. 0 effort approximately, and a factor of 50. So yeah, I rather like that. However, there are some caveats. So let's look at this code. So again, what is in red is changed or added. So rather than using NumPy, I'm using that cursed array thing in the Python standard library. I'm importing it here, and I'm initializing my array with this array function rather than using NumPy. Okay. Apart from that, I do the same thing. I just annotate with JIT and I'm done. So this is the only change. Okay. I would say this is a really, really minor change. Great. If you time that, then you see that unfortunately now the Numba version is in fact a little bit slower than the Python version. And the only change I made was the data type in which I stored those stupid numbers. Okay. So yeah, there are caveats here. You have to be a little bit careful what you do because you don't always get an improvement. So basically, apparently it's 20% faster. Problem is I can't read the numbers, so but yeah, okay. So this would be the Python version. This is the Numba version. Yeah, it's 80 something, 81 versus 99. So basically, you need 20%. The Numba is still 20% faster. Okay, great. But yeah, only 20% versus a factor of 50. So that's, of course, a huge difference. And that's just changing data types. So you have to be a little bit careful. Okay, let's take another example. And that would be computing Julia set. So you compute the Julia set by iterating over complex numbers or iterating complex numbers. Okay. So it's also a running example. So basically, as you can see, this is the pretty standard implementation. We have a for loop over our domain of complex numbers. So we do this for a large array. And we have this while loop here, which depends on two conditions. One is that the number of iterations is limited to a certain maximum. And the other is that the norm of the complex number should be less than a certain value. Okay. And the operation I'm doing is squaring the complex number and adding a constant to it. And this I keep on doing until either I run out of iterations or the norm of my complex number grows too large. That's essentially the idea. And what I keep track of is the number of iterations for each complex number. Okay. So again, simply annotating that with JIT, that's great. We get a factor of 1000. Well, okay, 912 faster than Python with zero code changes except for adding the decorator. So that's good. So question, can we do better? In fact, yes, we can. So basically what we can do is being a little bit less naive. So again, we use the JIT decorator, but we provide additional information. And the information we provide is the signature of our function. So basically the types of the parameters of our function and its return type. So let's have a look. The function doesn't return anything, so void is the return type. So yes, this is of course borrowed from C or C++. So basically this means no return value for this function. And indeed, if you look at the implementation, the relevant information is just stored in that array iterations, so there is no return value here. So that's the void, okay. Then we have a complex 128, so that would be the type of domain. And the column thing means this is a one-dimensional array. Okay. Then the second argument is, oh yeah, what is a complex 128? I should explain. So basically that's a complex number with double precision real and imaginary part. The 128 is the number of bits which is used to store that number, so that's 64 bits for the real part, 64 bits for the imaginary part. 64 bits, 8 bytes, is double precision, so that gives you 15 significant digits for both real and imaginary part. Okay. You can store values up to 10 to the power 308 in them. The smallest number that's larger than 0 is 10 to the power minus 308, etc., etc. Okay. So that's domain, one-dimensional array. Then you can guess that int32 is also going to be a one-dimensional array. Indeed, that's our iterations. And int32 is an integer type with 32 bits, 4 bytes, basically integers ranging from minus 2 to the power 31, that's minus 2 billion, up to 2 to the power 31 minus 1, which is plus 2 billion and some stuff. Okay, again an array. Then max norm is a float 64, so again double precision. And then max iterations is an, max iterations is an integer, again in int32. Okay, so great, this is a bit more work. And of course, I need to import stuff here. I need to import all these type designators, and I need to document or to specify my function signature. Okay, but I would argue not that much work. So the question is, what do we gain? Okay, so basically we gain a factor of 2.4, which is compared to the factor of 1000 with respect to Python, not that much. But then again, speeding up your application by a factor of 2 is quite interesting at the end of the day, especially since the effort you need to invest is not that much. So you end up with code that is actually almost 2,200 times faster than the original Python code. Okay, pretty neat, nice, and so on. So how does it work with the type mapping? And basically, if nothing is returned, so none if you want in Python terms, then you specify a void. Int in Python can be, depending on what you want, int 8, int 16, int 32, int 64, or uint 8, etc., etc. So basically, what does that mean? Well, int 8 is 8 bits to represent an integer. So that's values from minus 128 to 127. Okay. Int 16, okay, you can guess what it is. It's just 2 to the power minus 2 to the power 15 up to 2 to the power 15 minus 1, etc. Int 32, int 64, and so on. So the u variant of each integer type means that it's unsigned. So for instance, for uint 8, that means values from 0 up to 255. For uint 32, 0 up to 2 to the power 32 minus 1, so that's 4 billion and some loose change. Okay, so here is a little something to remember. Basically, in Python, an int is an object, and it doesn't have an upper limit. So an integer in Python can grow as large as you've got memory in your computer. So if you rely on that, you're going to be in trouble. Also, of course, you should be careful to pick the right integer representation for your task. Because if you take an integer type that is too small, then of course what will happen is overflow. If I take, for instance, say an int 8, and I've got a value of 127, and I add 1 to it, I can't store 128. So what's going to happen is that my value after the addition is going to be minus 128. You don't get errors about this. This is considered normal behavior in a CPU. So basically that means that you have to right size the type of your integers. On the one hand, you don't want it to be too small, because then you get overflows and probably incorrect results, unless you do that for some very specific reason. And of course, given that it's the default and that there is no error, there are many valid use cases in computer science and systems programming. But typically in scientific programming, you don't want this overflow to happen. It's probably going to lead to incorrect results. So on the one hand, you want your type to be large enough. On the other hand, of course, you also don't want your type to be too large. Because if it's too large, it wastes memory. If I know that the largest number I'm ever going to encounter in a certain problem is 100 million, yeah, why would I take int 64? I can store 100 million happily in 64. That's not a problem. But I can equally happily store it in int 32. And that's only half the size. So if I have a large matrix or large array with that data type, then of course that is going to be a significant amount of memory, which is just going to waste. So that's not nice, because typically in scientific computing, memory is an important resource and something not to be squandered. So yeah, you need that memory likely. And even if you don't really need it, then there is another consideration, and that is the time it takes to transfer data. Okay, transfer data where? Well, what you might think is that when you do a computation, that your bottleneck is the number of operations per unit of time. And of course, that's true at the end of the day. But what may happen is that the core itself, so the CPUs, could do many more operations, but that are waiting for data. And that means that your application is memory bound rather than compute bound. And most scientific applications are in fact memory bound. So they are bound by the time it takes to get memory from main memory to your CPU. So from your RAM to your CPU. That takes time. And in fact, that takes significant time. So why? Well, there is, on the one hand, there's latency. So what is the price I pay for a memory transaction, regardless of its size? That's one issue. The other issue is memory bandwidth. How many bytes can I transport per unit of time? Note, bytes per unit of time. Okay, so my bandwidth is finite. How many numbers can I transfer per unit of time? Well, then things get simple. I can transfer twice as many int32s per second as I can transfer int64s. Simple. So basically, if my code is memory bound, it's very much in my interest to make sure that memory transfers are minimized, or that my effective bandwidth is maximized, which I can do by trying to squeeze my types up to the point where it stores what I want to store, but doesn't waste memory. So that's essentially the idea, and that's why all these integer types are in fact there. They are supported in all lower level programming languages than Python. Python just has a single integer, which has nothing to do with any of the types on the right side of this slide. Okay, float. Again, you have two choices, either float 32 or float 64. Float 64 I already explained. That's 8 bytes for floating point number, so basically 15 significant digits. Float 32, single precision. So basically 7 digits of precision. The largest number you can store is 10 to the power 38. The smallest non-zero is 10 to the minus 38. So basically, again, a data type that takes less memory at the expense, in this case, of precision and of minimum and maximum values. Same story. If you can get away with using single precision, you're only using half the memory. You're effectively doubling your memory bandwidth. And there is another thing going on under the hood. So basically, when we did the back of the envelope computation, I already told you, okay, what I'm doing here is naive and actually not entirely correct. So a reason why it was not correct is that, in fact, if your code is compiled correctly, etc., this type of operation, like this matrix-matrix multiplication, is not going to be done element by element. It's going to be done in groups of elements. Because of factorization under the hood, we'll talk about it in the context of NumPy and some other frameworks later on as well. But basically it means that you can actually add or multiply 4 double precision numbers in one cycle, or 8 single precision numbers in one cycle, rather than just a single one. That's for all the hardware. For the very latest hardware, these numbers double. So 8 double precision numbers and 16 single precision numbers. Not always faster. Okay, lots to say about AVX 512. Different story, different training. But essentially, it is possible that if your code can be vectorized, that's something that NumPy will do for you automatically if it can do it. It can actually also speed up your application if you can use single precision rather than double precision. Can you do that? I don't know. It depends on whether you need 15 significant digits or not. If you don't need them, don't use them. Less memory, more memory bandwidth, more instructions per cycle. Easy. Well, more operations per cycle, let me call it that, because it's a single instruction. Okay. All right, then a 1D array, quite simple. For instance, float, then square brackets and column. 2-dimensional array, 3-dimensional array, you see where this is going. So basically, if this reminds you of slicing, yeah, that's where the notation comes from. It has as such nothing to do with slicing, but it's good visual representation of this. Okay, I told you the int thing, so that's it. Okay, something else NumPy is useful for, but let's postpone that till after the break. So let's have a break first, because we've been going for almost 2 hours, so time for coffee, tea, whatever you prefer. Let me see what the time exactly is at this point. Okay, so let's make that 11, because that's just 10 minutes, and that's fine. For the people in the room, if you like coffee, you can have some. You leave the room, you go to the left, you keep on walking until you hit a coffee machine. There are 2 of them, so you can use those. They dispense paper cups. Feel free to take coffee. It's literally for free. If you prefer soft drink, again, leave the room, turn left. But before you enter the cafeteria, turn right. There are vending machines, one of them for soft drinks, the other for snacks, I think. So you can use those, but those are not for free. Okay, so see you in, meanwhile, a little bit less than 10 minutes.
question.
Yeah.
What are we discussing CubePy today?
Sorry.
CubePy.
No, that's Python on GPUs. That's for Thursday.
Oh, that's what Thursday.
Yeah.
Okay, perfect.
So today is CPU only, and the GPU part is separate. I'm still in two minds what to do, whether to fuse this training or to leave it separate. There are arguments for both. So up to this point, I've not decided to put it together into one training because there are a number of aspects in this training which are not necessarily useful for people who really want just to do GPU programming and vice versa. So that's why I keep it separate and probably will be keeping it separate in the future as well. Yeah. What I need to figure out is the relationship between the domain and the right, because I believe that this is okay, we don't need to do that's programming easy. For people in mind, this is sometimes a bit of a problem because they don't necessarily have first name, last name, and it requires a bit of how shall I put it? All right. Okay, this is what we go through. What the first one is because he did it this is part of it. But I need to move it. So this one, I'm not so you know this one? Yeah. Oh, everything. So I've got two names here. So that's probably yeah. Okay, administration figured out. So let's restart. Are there any questions up to this point? We're not quite done with Numba yet, but okay. If not, wait, I have to make the chat visible. Okay. If not, let's continue. So what else can you do with Numba besides speeding up stuff in Python, which is of course cute? Well, you can also create ufuncs. Okay, what's a ufunc? A ufunc is a universal function, and that's essentially a function that you can apply to a NumPy array. So a ufunc is a NumPy thing. It's a function that you can apply to a NumPy function, to a NumPy array. And of course, you know many ufuncs because, for instance, np square root is a ufunc. So you can create your own. NumPy contains documentation on how to do that. If you read that documentation, you get probably a little bit discouraged because it's really not so very trivial. There is a lot of boilerplate code going on, which is essentially boring, but which looks rather intimidating. So, yeah, question is that necessary? According to the Numba people, no, because it can be simplified considerably using Numba. So basically, what are ufuncs? As I said, they can be element-wise functions that work on NumPy arrays, but they also support reductions, accumulations, broadcasting, and so on. So basically that means that I can do things like a sum. That's also a ufunc. Or a sum on the rows only, or on the columns. So all these things are ufuncs. Okay, and if you check the documentation, you will see that there is documentation to do that in C. There is template code, boilerplate code, and so on. But yeah, it's not particularly interesting. You can also do that in Cython, which I'm not going to cover here. I'm going to talk about Cython, but not that aspect of Cython, I think. Or do I? Don't quite remember. But anyway, how do you do this with Numba? Well, basically, again, two decorators, vectorize and GU vectorize. So vectorize will create a ufunc, and GU vectorize is going to create a generalized ufunc. We'll see examples in a minute. So here's an example of GU vectorize, and as you can see, it is similar in spirit to what we did with the JIT decorator. So essentially what we need to do is to specify the signature of our function. Okay, so let's have a look at the function. What am I doing? Well, you recognize the code. This essentially is, again, my Julia set thing. So this ufunc, or in this case generalized ufunc, is going to be pretty neat. What it's going to do is you can just give it a NumPy array of any shape, and it will do its thing. So that sounds like a nice thing. Not so very useful, but well, okay, let's not go there. So what do we have? With respect to differences, as usual, differences are in bold and in red. So basically, as you can see, we have the decorator and we have the function signature. In fact, nothing much changes, except that you notice something that's at first glance a little bit weird, because now all of a sudden, the two constants which we had, so the max norm and the max iterations, are suddenly arrays rather than scalars. So that's a little bit weird. Then something else changed. I've moved the argument, so the iterations parameter, I've moved it to the end of my parameter list. So those are the two changes with respect to the signature of the function. Okay. Still, it's a void function, so it doesn't return anything. And then there is a second argument to this GUFunc specification, and that's this string here. And again, it applies to the signature of the function. So again, it's information about the parameters. But now not about the type, but rather about how things are broadcasted. So essentially, what I'm saying here is that domains is indeed an array, and that has the same size as iterations and the same shape as iterations, and that the max iterations and the max norm should in fact be treated as scalars. Okay. All right, that's almost the only change. Well, a few more. So basically now I'm initializing iterations I to 0, because that happened, I think, in the calling code before. And another thing I do is I have to make sure that for maximum iterations I use element 0. It's going to work without that, but there is going to be a performance penalty if you forget this index 0 thing. Okay, so what do we gain? Well, we get something nice. We get that it is 1680 times faster than Python. So, okay, just for the Julia set, this is actually not so good, because basically this is slower than what we got with the just a JIT annotation. But yeah, this is a different thing which we're doing. We're operating on NumPy arrays now. We now have a ufunc to do that. So what we do is different. So it's comparing apples with oranges if we say that this is slower. More is going on. So, okay, we can't expect the same performance numbers, but it's in the same ballpark. So that's already good. Okay, so that would be the return type. That's the last parameter of our ufunc. And then don't forget, the snail means it will work without this index 0, but it's going to be slow. So if you see this snail, that means a performance thing. And yeah, this is easy to forget because, of course, you think of max iterations and max norm as scalars, as values, rather than as arrays. So it's something that you need to remember to insert. And then you can simply call the Julia ufunc on domain with the parameters max norm and max iterations, and you will get iterations, so an array with the same dimensions, with the same shape as the original domain. And max iterations and max norm can just be numbers. So they can be, you don't need to do anything special there. Okay, that was easy. And basically, you get automatic broadcasting, because that is what the whole shenanigans here give you. So that's the broadcasting definition here, or the broadcasting specification. Okay. So yeah, pretty easy to create a ufunc. Compare that to the usual way, writing a C implementation of this, and then writing the glue code, so the code to interact with NumPy, and you're busy for a couple of pages, while here it's just fiddling a little bit with your code, and then adding decorator and you're done. Okay. So basically, Numba is indeed, I would argue, pretty easy to use. If you just use the JIT decorator, you already get a speed up. If you add signature information for the compiler, you get a better speed up. So it's kind of really easy. It's also very easy to create NumPy ufuncs. The problem with this is, of course, it's a black box. You get some C++ code. You can look at that. That's not the point. But it's generated code. In general, looking at generated code is not so trivial. So that's definitely a drawback. It's a black box. And of course, you need Numba. Is that a drawback? Well, not necessarily. But you have to make sure that it's clearly stated that your application needs Numba, that you have an environment definition which contains it, and so on. Apart from that, it's not really a drawback. It has a number of features which were not covered, one which I already mentioned a couple of times. You can use this to generate CUDA or HIP code. And what you also have is automatic parallelization. So that's not in the slides, but we can have a look at the notebook. Let's do that later on. Remind me to do that. I don't want to do it now because I first want to finish the part on speeding up serial code and then talk about parallelization. It's okay, it's not fantastic. So yeah, your mileage may vary. Okay. So the CUDA thing will be covered on Thursday in the training on CUDA. Okay, any questions about Numba before we switch to Cython? No. Okay, so another way to speed up things is using Cython. So that's essentially Python with, again, sort of annotation. Now the emphasis is on annotation, not on decoration. So this works differently. But actually, it's kind of similar. So what you do is you add type information to your Python code. Okay, and that is going, at least in part, also going to be compiled to C, and it's the compiled code, the machine code that you're actually going to use. So it's in that respect similar to NumPy, but it gives you more control. And under the hood, a shared library is built which you can actually easily reuse without having this upfront compile step which you have with NumPy. You can do the build in advance during installation. So, of course, the question is there return on investment? In other words, how much do I gain and how much do I need to invest? What changes do I need to make to my code? What are the implications of using this technology? Okay, so same example, same motivating example, our prime numbers. So as you can see, in this particular case, we are doing the same test. Prime C, in this case, is a Cython version. Prime P is the vanilla version. Okay, so essentially, we get a factor of 72. Remember, with NUMA we got 54. So, okay, this seems promising. We even get a bit better performance than with NUMA. That's kind of interesting. Of course, again, it depends. It's much faster, but how much do we need to make changes? How many changes do we need to make to our code base? How difficult is this to do? So let's have a look. You already know the function. Okay. So in this case, this is just a simple list rather than an array. Okay, it doesn't make much difference in this case. So this would be the Cython version. Again, as usual, changes are red and in bold. We import Cython, okay, and then for primes, we specify the type. So basically, it's a Cython int array of 1000 elements. Okay, so that's already a difference. And then we check something, doesn't matter. And then we have to make sure that things are compatible. So if this is not compiled by Cython, that may happen, that the Cython compiler decides, okay, I'm not going to do anything with that, then I have to make sure that primes is correctly initialized. And in that case, I just assign a list of 1000 zeros to it. Okay, so we hope, of course, that this is not executed. Okay, then we specify the types of our local variables. So n and n found are both integers. We specify that here. Okay, and apart from that, only at the end something changes. Basically, again, I'm going to make sure that what is returned is in fact a list. So it's just a list comprehension to ensure that we get the right output. Okay, so again, not that many changes. We added type information. And of course, in our function signature, we did similar. So we specified that the number of primes, I forgot to mention it, is also an integer. So just adding type information. A bit more work than NUMA, but I'd say not significantly more. But of course, there are sort of breaking changes. This can still be run with Python without compiling, but of course we need Cython installed anyway. So, okay, there is a more significant code change here. Okay, so how do we make sure that this compiles? Well, basically we need a setup.py. So that is Python's build script, if you want, for installations, for non-trivial code generation and so on. Okay, so we import some things, and then we say, okay, we create an extension module, or rather, which is Cythonized this particular Python file, and we have to specify the language level, which is Python 3 str. Don't remember what it stands for, but basically, this is the right language level in order to get modern things. Okay, so we run that simply, that setup script. We build an extension and we do that in place. So basically the extension is going to be built in the directory I'm running the setup script in. That's what the in place does. All right, and then I can use that as if any other Python module, no problem. I just import it and I can just run it. So quite simple. I'm assuming here that the first argument of my script is going to be the number of primes I want to have. Okay. If that's not the case, then of course this fails, but yeah, don't do this at home. Don't use sysargv, please. Bad practice, but just for brevity, I do it here. Okay, so pretty straightforward, but a bit more work. More type annotation, more scaffolding. We need this setup.py. We need to remember each time we change the primes.py file that we also have to rebuild the extension, because the step to build it is now manual rather than automatic as it used to be in Numbat. So yeah, that's a bit more scaffolding. Okay. Of course, build tools like make, CMake are your friend here. For simple things, it's not necessary, but if dependencies get a bit more adventurous, then you really want a tool like make or like CMake to control your builds, so that things are a bit easier. Okay, so this is new style. Old style would have been a PIX file. So that would not be a Python file, that would be really for Cython exclusive. And it would have looked like this. Well, it would not have looked like this because that's our Python file. So this would be the PIX file. And you notice a number of differences. So there is a non-Python keyword here, which is cdef. See? And this you'll use in order to do the time definitions. Of course, why does it exist? Well, it's for historical reasons. So basically, back in the days, a long time ago, before Python had type annotations, there was no way to legally in Python specify a type. So the Cython people, which have been around much longer than the type hints, basically said, well, okay, we need some syntax. We will just create a sub-language, a new domain-specific language, in which cdef means something followed by a type, and then a variable, and that's going to be our type declaration. So basically, in all our examples and tutorials for Cython, this is what you're going to find. With, if memory serves, Cython 3, the new syntax has been introduced. So of course, for new development, don't use PIX files, use Python files, use the modern notation. Note that it is a little simpler in the sense that, of course, you don't need to bother whether it's compiled or not, because you can only execute a PIX file when it is compiled, period. Also note you don't have a Cython import, so there are differences which you need to take into account. Okay. Now, one of the things that I mentioned is, well, yeah, we want to profile before we start doing stuff. So, of course, if you want to optimize your Cython code, you also need to profile. And then the question is, what do you do? How do you do that? Because Cython functions are not going to be visible to cprofile. That's a little bit of an issue. So you need to do a bit of extra work. What do I mean? For instance, this function here, this sign2 in this PIX file, is not going to be visible. So in this case, it will show integrate because that's a pure Python function, but it's not going to, well, it's a function that is going to be a Python function. Sin2 is not. So basically, Sin2 is only called in this Cython function, and hence it's not going to be part of the profile by default. So that's a bit of a problem. So you can switch on profiling explicitly, and that's easy. You just add #Cython, profile is true, and then this function is going to be profiled, and you will see all the calls which are essentially in that C function at the end of the day. So you can do that either at the level of a file with this directive, or you can do it with a decorator with the profile is true decorator on a function by function basis, whatever you need, whatever you want. Okay. So if you call Python functions inside, they may disappear from the profile as well. So profiling Cython is a bit more challenging. You have to be a bit careful interpreting that. Okay, so basically what you can do is run a script with Cython annotate, and that is going to create an HTML file, and that is going to give you an indication which functions or which lines of code are good candidates to convert to Cython. So basically you will get something like this, and yellow means pay attention. Pay attention in the sense that this is computationally heavy, this is that you might want to turn into Cython. And indeed, as you can see, this is a good candidate for that. And the more yellow, the darker yellow, the computationally more intensive that this code happens to be. So this is just going to generate an HTML file which you can view in your browser and just see what went on. Okay, so this is for a very ancient version of Cython, but yeah, it's just updated, so no problem. Okay. So basically, why do we need type annotations? Again, same reasoning as for Numba. The more information you give a compiler, the easier it is to generate efficient code. In case of Numba, it was optional. In case of Cython, it is sort of optional. So basically, use the Cython module for type declarations. So essentially, in this case, I and j would be Cython integers. So this is for local variables. This would be an array of 100 double precision numbers. Notice the difference, no float 64, this is double. Why? Again, historical reasons. So basically, the type system of Cython is that of C, so it's a bit older than the C++ one. You do have double in C++ as well, but you also have the new type names such as float 64 and so on. So basically that's the reason for that. Okay, function parameters similar. So basically you just use Cython int. And of course, if you're familiar with type hints in Cython, you recognize this. It's the exact same thing, except for arrays, of course. But for normal variables, it's the exact same as you would do with type hints in Python. So that's a very nice thing that the Cython people decided to adapt to new language features and make the Cython quote-unquote syntax compatible with Python type hints. Okay, so there are a number of Python types that have Cython equivalents, so direct implementations in C, and those are the standard types like lists, sets, dictionaries, tuples, and so on. So basically, if you specify for Cython results list, that is going to be an implementation that is specific for Cython. So basically, it's going to be a fast implementation of a list. Okay, so that ensures that specific code is generated to deal with lists rather than other data types. So that helps. Specialization always helps. Okay, so it's all defined at compile time, of course. So for picks, basically you use the cdef Cython keyword, and you would get this notation, so cdef followed by the type, and then the variables you want to declare. The function signature is slightly different, so you precede the parameter with its type. So this is the same as you would do in C. So many old-style Cython syntax is in fact just derived from what was done in C, or what is done in C. Okay, so basically you do have the same thing. You can use lists and sets and so on, and again, specific code is generated. Okay. Type mappings, so similar to null, of course. A bool is a bint. An integer is again a short, an int, a long, long. So those are the C types, not the C++ types. So it's a little bit different. Actually, in C, you don't know the size of a short. You don't know the size of an int. You don't know the size of a long. The only thing you know is that the size of short is less than or equal to the size of int. And that the size of int is less than or equal to the size of long, and that the size of long is less than or equal to the size of long. That's the only thing that the C specification specifies. It doesn't say how many bytes an int a long or long has. So yeah, that makes your code a bit tricky. So you need to check first what are the how are types actually implemented for your particular compiler. Typically, emphasis on typically, int is an int32 and long is a int64 and short is whatever. Okay, then float comes in float and double. Float is single position, double is, yeah, well. Complex also comes in float complex and double complex. No surprises there, but this is C, so basically under the hood, the complex number is going to be represented as a struct. Then bytes and strings are represented as characters or in C++ std strings, and dictionaries are represented as structs. So that's basically the idea. That's basically your type method. So the fact that there is struct here already gives us a hint that we have to be a bit careful with dictionaries. Okay, same caveat applies. So basically the C or C++ code can overflow for integers. That's similar as to number, so that is just repetition. Okay, so for those of you who are familiar with C, one of the nice things in C is that you can do dynamic memory management. So you can create an array of a certain size. Once you don't need it anymore, you release the memory, and it's free for other data structures. So that's a very powerful feature, something that Python tries to do for you automatically, and sometimes miserably fails to do. But basically in C, you have control over that, and you have to do that manually. That means that you need to be able to do a certain number of things. One of the things is changing types. So basically typecasting is changing a value into a different value. So in C, it would be A it receives the value of B when it's turned into an integer. So in Python with Cython, you use Cython cast. You specify the type and the value you want to cast into that type. In Cython, so basically in pixels, you would do it using this notation. So these weird with the less than, larger than. Okay. So you can do type aliases. Basically, real would be another name for double. That's what this type def in C says. So you can do the same thing in Python. You can say Cython type def. A double has as an alternative name a real. And for pixels, it would be C type def double real. So exactly the same as in C, with the C prepended to type def. Okay. So basically, why is this here? Okay. This was the original slide, and I took it apart into two slides, and now I forgot apparently to remove this guy. So let me add that to the remarks about these slides because I want to change that. Okay, so that would be slide 40. Okay. Something that I missed when I was adapting the slides for the new. So a Cyton structure, again, CDEF struct, particle, double X, double Y, and int charge. So this is a bit like a Python tuple in a way. So essentially you have different fields, but those fields have names and they can have their own type. So I have three fields here, X, Y, and charge. The first two are floating point values. The last one is an integer value. So this is like a dictionary, sort of, but not quite. Okay, so the block structure is like Python. So this is the struct definition. These are the fields. Indentation matters here. Okay. So in your PIX file, you can use that. For instance, you can say particle P, and then that's going to be such a struct with X, Y, and charge elements or fields. And you can just use P.X, P.Y. So yeah, this might remind you of classes in Python, or named tuples if you like. So there are a number of analogies. Okay. For C programmers, in C you would have to write struct particle. That's not the case in Cyton. Just particle is enough. Okay, if you would use that in a Python script, so we import the particle module, and then we just define a particle as a dictionary, and we can compute particle distance on P. So basically, that would work quite well. Okay, how do we do the same thing, but now in modern style Cyton? Basically, that should not be in particle PIX, that should be in particle pi here, so that's a typo. 50. Okay, so declaration is very similar, only of course we use type hints in Python. So basically we define these as lots of typos because there's a minus sign here, which of course can't be. So basically we declare these fields here. So this should also be an equality sign, not a minus sign. Okay, then we can simply use them. Just the usual type hints in Python, no problem. So basically, same thing here. We declare it as a dictionary, and we can just call this function, which is defined in particle.py. Okay. So we always have these two views: old style Cyton and new style Cyton. You might wonder why am I talking about old style Cyton? There are still a few things which you cannot do in new style Cyton. That's why, if you would use Cyton, you need to know both actually to be productive. Okay, so one of the things in C, as I already mentioned, I was a bit too early before, is basically dynamic memory management. So essentially, you can ask for memory. You can ask the operating system for memory, and it's going to reserve memory for you and give you the address of the first element. And that is stored in a special type of variable, which is called a pointer. So that's just a variable that can store an address for data of a given type. So in old style Cyton, that would be cdef int star p a. So p is a pointer, a is not. Okay. So there is the address operator, and that's the ampersand sign. So ampersand A gives me the address where a certain integer is stored. Okay. How do I get that value? Well, I can, for instance, add 1 to the location in memory where A is stored by adding that to P0. Okay, that sounds a little bit weird. Why do I need a 0? There are technical reasons for that. I'm not going to explain them here, but C programmers will know why that why there is this P0. Okay, so in C itself, you would use this notation. In Cython, you have to use P0. The two are, in fact, if you are a seasoned C programmer, you know that those things are the exact same. So that's why it doesn't matter in C, but it matters in Cython. You would have to use this notation. Okay, how do we do that in the Python thing? Well, basically easy. There is a special type, pint. So that's a pointer to an integer. So no stars, no nothing. Much easier. We just have a specific type for it. The address operator, there is none. So it's simply a function, Cython address. Okay. And then the referencing is actually the same. So again, in order to use the address stored in P, we use P index 0. All right, so that's something to note that you need to remember. So one of the reasons why you still need to know the old style definitions is that currently in new style Cython, there are no function pointers. So basically that means passing a function to a function is going to be problematic. So that's why you still need to know about old style, because there you can do it. In new style, you at the moment can't. So they have to come up with a solution for that. Okay, time to talk a little bit about the buffer protocol. So the buffer protocol essentially exposes the data stored in data types such as arrays, NumPy arrays, byte arrays, etc., etc. So they give you direct access to the actual data. So many things in Python support these. So this is all in the Python standard library, but also in NumPy. And you can easily get that by using the memory view function. And then you can use that in order to directly use C code. So for instance here, we have a Python array of double precision numbers, 1000 in total, initialized all to 0. And now I can pass a memory view to that data to a function. In that function, I've got an array, and here in this case, I can check the shape of that array. So basically that gives me, since it's a one-dimensional array, it's going to give me the length of that array. And then I can initialize the array elements in some way. So this is a very direct way of interacting with things that support buffer protocol, all types of arrays. So basically, here's a NumPy example. So basically, I've got a cdef function, and it's an array sum function. So basically, it gets an array. What this notation means, I'll come back to, and that's a memory view. Okay, and then I can simply iterate over my memory view. I get shape 0, so the number of rows. I get shape 1 of my memory view, the number of columns, and I can simply iterate over it, computing the sum of this array. Of course, this is a bit waste of time because NumPy has a sum function, so yeah. Anyway, in fact, it's not that bad. because it's almost as fast as NP sum. So if I run this and I compare it to NP sum, then results are very similar. So NP sum is faster, but not by that much. So that's actually quite nice because it shows that Cython can generate some quality code, let's put it that way, without too much overhead. Okay, so what does this mean? Basically, this notation means that this is a two-dimensional array and it is C-contiguous. What? Well, basically you have two choices. Either you store two-dimensional arrays by row or you store them by column. So basically, memory is a one-dimensional thing. So a two-dimensional thing needs to be flattened into something one-dimensional. So yeah, it's clear you have two options. Either you store row number 1, then row number 2, then row number 3, etc. Or you store column 1, followed by column 2, followed by column 3, etc., etc. Okay? Both choices occur in practice. So if you look at C, if you look at NumPy by default, if you look at Python, if you look at C++, those store in row major, so basically row by row. Fortran, Julia, R, MATLAB store column by column. So it's clear that you need to know, and it's clear that you need to tell the compiler, because otherwise you will get results which are potentially incorrect. Here, of course, it wouldn't matter because, well, yeah, it would matter because I could get a segmentation fault, but basically this is something that I do in for all elements. So whether I go by column or by row doesn't make a difference. But still, to get my dimensions right, my shape right, I need to do it the right way. So this basically means that the columns have stride 1. If you think of slicing notation in Python, then this is the beginning, the end, and the stride. So the stride for the column is 1, which means if I move 1 byte, if I move 1 unit, I go to the next row element. Okay, so easy for Fortran layout, very simple. You swap the two. So now to go to the next row, I just need to move one memory location down, or okay, actually right. So the stride is on the columns rather than on the row rather than on the column. Okay. So memory views in general with NumPy arrays. So we create an array with NumPy, usual way, and I can create a memory view out of it. And then the number of dimensions is MV and dim. So for two-dimensional array, that would be 2, etc., etc. One-dimensional array 1, and so on. I can get the shape, which will give me a tuple. I can get the format, which will indicate which type the elements are. So D means double precision floating point, F means single precision floating point, and so on. Then the data size. So that is basically the size in bytes of an individual element. So this is double precision numbers. So that means 64-bit or 8 bytes. Hence, in this case, 8. Then the number of bytes, yeah, that's just the size of the whole thing. So that's basically the number of rows times the number of columns times the size of an individual element. And the strides, which also tells me, this is expressed in bytes, whether I have row major or column major. Okay, you can make a memory view read-only, so you can check on that, whether it's read-only or not. in this case, it's by default not read-only, of course. So basically, that are memory views. And that makes it very easy to bridge any type that supports the buffer protocol with C or Cython code. So this is a quite convenient thing. And if memory serves, we'll talk about it again later. So in Cython, you've got 3 types of functions. Basically, you have pure Python functions. Yeah, there's nothing to say about it. You use the def in order to define it. And they can, of course, be called anywhere, and they are at Python speed, so potentially slow. You have pure Cython, so those you get by using cdef rather than def. So those can only be called from within Cython, and those are hopefully fast, and of course they have C semantics as well. Okay, and then you have Python plus Cython, so cpdef. So they can be called anywhere, also in Python, and also in Cython. And they can, of course, then only have either Python arguments or types which are easy to convert to Python types. So no pointers, things like that. And they're still pretty fast. They are a bit slower, of course, than cdef functions, because cpdef functions, by their nature, need glue code in order to convert function arguments from Python into C formats. So they are a bit slower. That means that basically your outer layer of your API, so what you want to expose to Python, should be def or cpdef, and everything that needs not be seen from Python can be cdef, and hence a bit faster than what you can do with cpdef. So that's essentially the design thing. Okay, so if we do this in pure Python, yeah, for pure Python it doesn't make any distinction. And in the pure Python thing, we get decorators. So this says it's a C function. So this is, again, a pure Cython function. Or it is a Cython call function, so basically a CP function, which you can call from anywhere. So this is just modern Python notation of the same thing which you have in Pixar. Okay. Cython function signatures. So basically, the type we know. For this again, pix, and the return type is here. So basically, you can add inline. So that tells the compiler, if it's a small function, don't do a function call. Just anywhere where this function is called, insert the body of the function directly. So that can make sense. Typically, the compiler is going to do a good job automatically, but you can indicate that it's into the compiler that it may do that. Okay, so if you want to do that, that's just cdef inline, and then int, name of the function, your parameter declaration, and so on. Okay, so in Cython, you just use type hints, both for parameters and for the return type. So nothing special happens here. Basically, optionally, again, you can add inline. So in that case, of course, it's an additional decorator, and you can stack these decorators. Like you always can in Python, you can stack as many decorators as you want. So Cython inline is just an additional decorator. Okay. All right, then error return values. One of the problems with Cython is if an error occurs, it's just a warning in Python. So that's a little bit annoying. That means that you would need to be a bit careful there. So it's not going to be called by try except. That's nice. And you get nonsense as a return value. This is great. So something awful goes on. No one tells you, and you get nonsense. Oh, this is so nice. Okay, so that means you need to be a little bit careful. So essentially that means that if you know that something can go wrong, potentially in your citing function, you need to add an except clause. Okay, and then they are propagated. So here in this case, we have a PIX definition, let's put it that way. So cdef, and then you see this except with a question mark minus 1.0. Okay, so basically, this minus 1.0 need not to be returned by the function if something goes wrong, but it will be the value which is returned automatically when something goes wrong. So basically, you need to pick that value judiciously, in the sense that it should be a value that is typically not a regular value. So in this case, I'm computing an average, and of course, potentially that could be negative, but I'm assuming here that it will not be -1 in a sense. So basically, if that is the case and -1 is a value that could be a legit return value, then you have to add this question mark to accept. So if you don't add the question mark, the -1 value should not be a valid value returned by your function. If you add the question mark, it may be. So why do we do this? Why all these shenanigans? Because why not just have the question mark thing by default? Well, the question mark thing means that extra code needs to be generated in order to distinguish between regular return and something blew up. And that, of course, takes time. So if you know that there is a function value, a data value that is never returned by your function, then of course you can just use that for signaling and no extra code needs to be generated. If there is none such, as in this case, then extra code needs to be generated and you indicate that by the question mark thing. Okay, so basically in pure Python, you get an additional decorator, except val, and again, same semantics. If check is true, that's the same as adding that question mark thing. And again, you just stack decorators as required. Okay. Any questions up to this point? I'm not so happy, to be honest, with this part of the slides because of the double syntax. That's really annoying. I hope that the citing people make more progress and that I can drop all the big stuff because it's just overload. Question.
In which cases do you want to do NumPy versus citing?
Okay. So in which cases do you want to do NumPy versus citing? You would do citing for two reasons. Well, for many reasons. NumPy is a black box, so you don't have any control. Citing gives you much more control. Also over memory management. So you can allocate memory dynamically with citing, which you can't do with NumPy. So that's already one argument to use citing. Citing, given that you have more control, also gives you potentially better performance, depending on circumstances. It may be that NumPy just outperforms citing in some cases, but in general you would get better performance. So that's basically the reason. It's more involved, you need to know more, it's more changes to code, but the return on investment is a bit bigger. Well, okay, no, not the return on investment. Your potential performance gain is a bit bigger. Is that better return on investment? That depends. Because yeah, development time is going up here. Cython is more complicated than Numba. There's no discussion about that, no getting around that. It would be silly to claim otherwise. So yeah. Also, there are a number of things which you can do in Cython that you can't do in Numba. For instance, we can have Cython classes. So these extension types, which I will talk about in a minute, and that's something that you don't have in Numba. Okay. So basically, CDEF classes or extension types. That's essentially a class which is going to be a C++ class or C thing, which represents that back in the old days, and of course that would resemble a Python class. So this is just a pure Python class. It's old style in the sense that we have a doubler in it, etc., and it has certain methods and so on. So that's what you're used to. That's just Python. How would you turn that into a Cython class? Well, pretty straightforward. There are not that many differences. And for once, they're not in red. Don't know why, but at least they're in bold. So basically, you add CDEF in front of the class declaration, and then you would also have to add the type information for all the members. So yeah, that's the difference. Easy. This goes into X file, of course. So basically, this is the object attribute declaration, and that's the assignment. So basically, the definitions of them. So you have, as usual in C or C++, you have declaration versus definition. So the declaration is just which type are they. The definition is which values are they going to have. Okay, there are differences. So basically, in a Python class, or in a Python object for a certain class, you can access anything you want. All the attributes, you can just access them. That's not the case in Cython by default. So for CDEF class, this is different. So what you can also do, if you have an arbitrary Python object, whatever it is, you can always add a new attribute just at the object level, the object itself. So that means that if I have two objects of class A, that one can have an attribute that the other does not have, because I just added it at runtime at some point as a whim, I can do that. Which is nice, but which is also dangerous, because a typo means interesting debugging, etc., etc. So that is something that you cannot do in Cython. You can't at runtime just add an attribute to a class. That's not possible. Why? Because creation happens, or definition, declaration happens at compile time, not at runtime. So basically, if you look at a Cython object, its attributes are going to be in a dictionary, dunder dict, or dunder slots, whatever, but normally if you don't do anything special, it's going to be in dict. In Cython, it's going to be in a C struct. So that's the difference. And of course, a C struct can't be dynamically changed. That's something that is fixed at object creation, and that never changes during the lifetime of a C struct. That just can't happen. So that's the difference. Okay, so Python extension types essentially quite similar, but of course, as usual, we annotate the class, we add a decorator to the class, and we add some type definitions, but in Python style. Okay, so again, nothing special is happening, and of course, we have all the same things which are happening here. Although there is no CDEF here, this is still called the CDEF class, just for historical reasons, because that's at the end of the day what it is. It's an extension type or a CDEF class. So basically, Although there's no CDEF here, it's still a CDEF class. Okay, so I mentioned that the object attributes can't be accessed. Is this a feature? Is this a bug? I'd consider it a feature, because basically that means that I can control access to the attributes, which in Python I can't. Can never prevent someone from accessing an object attribute or from modifying it. So potentially that can create a number of issues, bugs, and so on. So by default, that's not the case in Cython. So by default, object attributes are private. So in this case, n would be private. And now I have a choice. I can make it read-only, so that's nice. I can get the value of the n attribute, but I can't assign for it. That's actually rather nice. Of course, within the class itself, methods in the class can, of course, both read and write these attributes. That's pretty obvious. Or I can say it's public, and then it can both be accessed, its value can be accessed, and its value can be modified. Okay, again, same thing in Cython. So then you use Cython declare, and you specify the visibility. And the visibility is again the same thing, either read-only or public. So this gives you much better control over what you can do with your object attributes, which is actually a very nice feature in a way. Okay, so getters and setters, both in Cython and Python, you can use add property for the getter and then the setter. So each time a decoration, so that would work in both, that doesn't matter. And then you also have a deleter if that's appropriate. Don't see that much in code, but oh, if you need it, it's there. Okay, dynamic memory allocation. So that's one of the things that are specific to Cython that you can't do in Numba. In Numba, it may happen or not, we don't know. But in Cython, you can control it. So basically, if you need memory when you create an object, for instance, your object internally uses an array in order to store data, and the size of that array is not known at compile time. So it can change from one object to the other. It's part of the initialization code of that object. In that case, you can do that in the dunder cinit method. So note, this is not dunder init, this is dunder cinit. I'll tell you in a minute why there is a distinction. And then you can use, for instance, malloc in order to create a data structure with a certain size. So why is it cinit, and why you really shouldn't do that in init? Well, init, dunder init may be called multiple times in some circumstances. Not necessarily a brilliant thing, but it happens in Python. While dunder cinit is guaranteed to be called only once. That's for sure. That's a given. Why is that important? Well, suppose that I ask for memory, and I would do that in init. Okay, I ask for a gigabyte, but due to some Python fluke, that init method is executed multiple times. Yeah, then I ask for a gigabyte, and another gigabyte, and another gigabyte, and I'm never going to give them back to the operating system. So I've got a memory leak. So that's why it's crucially important that this cinit is called exactly once, and that you shouldn't do memory allocation in init. That's the reason. So it's to avoid memory leaks. The reason is each malloc is paired with a free. So malloc is I ask for memory, free is you can have it back. The you in this case is the operating system. Dynamic memory allocation, 2 steps, getting it, releasing it. Okay, so the freeing of the memory, that's in the dunder dealloc. And that's, of course, both cinit and dealloc are specific to CDEF classes. That's pretty clear. And again, it's guaranteed to be executed only once when the object goes out of scope, when it's destroyed. And again, it should be called only once. Because if you call free on memory, on a memory location that's already freed, you get a segmentation fault. So again, it should happen really once and only once. Otherwise, your application will horribly crash. Okay. Inheritance. So if you want an object or class hierarchy, you can do that with extension types, with CDEF classes. So a CDEF class can inherit from a single superclass only. So that's different from Python, because a Python class can inherit from as many as you like. If you want to make your life complicated, multiple inheritance is a thing. But in Python, it's just a single class it can inherit from. So it's either a built-in class, and I think that built here should be written with a T, not a D, but that's irrelevant. So basically, any object or extension type, but it cannot be a regular Python class. So basically, you cannot create a derived class in Python from a Python class you defined. That's not an option. Okay. Python classes, on the other hand, can inherit from extension types. So Python class can inherit from a CDEF class. That is possible. But of course, it can't use CDEF methods from its superclass, because now we're in Python world. CDEF was pure Python. So I can't call a CDEF method from a Python class. Context is different, can't do it. So that is a limitation, and that is weird, and that is actually breaking an important principle of object orientation. This is breaking Lischkov's principle, so this is actually bad, but okay. And you can't override CDEF methods from the superclass, so that makes it even worse. Okay, whatever, that's life. Okay, so basically, now we're sort of moving into parallel programming. One of the things that you may be aware of is that Python, at least up to Python 3.13 and including standard installations of Python 3.14, has something which is called the GIL, so the Global Interpreter Lock. And that ensures that only a single thread can access an object at any given time. Which is a good thing, because that means that you don't have race conditions and that you can't have deadlocks, which is great for correct programming. It's not so great for performance. So that's why in Python 3.14, it is optional at installation to get an install, to get a build, which disables the global interpreter lock. Okay. I not recommend to do this at this point in time, because many libraries are not ready for this. So you might get really, really weird behavior if you disable the GIL. So I'd say don't wait a while until this has stabilized a little bit. Because basically, as you may know, Python 3.14 has been released like last month. So yeah, well, okay. So I'm not going there under any circumstance before I'm 100% sure that the libraries I rely on actually will work properly with that type of installation. Anyway, so basically most things in Python are, because they don't need to be, not thread safe. Okay, so basically that means that it's only safe if one thread accesses an object. So that's quite okay if you have operations with high latency, I/O, network operations, whatever, things that are uninteresting for scientific computing. But everything where we care about performance and multiple threads, of course, this becomes very annoying. And basically, that means that something needs to be done. This is a problem for scientific computing. And of course, the Python community acknowledges this, and hence it's trying to move away from the GIL, but as I said, this will take a few iterations before that is reliably done. Okay, so how can we do that? How can we sidestep this? And this is also something that Roomba can do without you controlling much, but that you can do explicitly in Cython. So parallelization, using multiple cores in your CPU. Okay, under the hood it uses OpenMP. So open multiprocessing, so essentially that is a standard, which you can check. At the moment it's 5.2 if memory serves, and basically it gives you a list of a number of things, compiler directives for C, C++, Fortran, and a number of library functions. All reasonable compilers support it. GCC supports OpenMP, the Intel compiler supports OpenMP, etc., Clang, and so on. So for shared memory programming in C, C++, and Fortran, that is a very classic way to do that in scientific computing. So it's your typical go-to for shared memory programming. It can do GPU offloading, which is nice, especially since it can do it for Fortran, for C and C++. So basically, it's a very nice standard. And again, okay, your support for CUDA offloading is going to take a while, but at least NVIDIA compiler does a quite reasonable job at it. Okay, so how can we use this in Cython? Well, there's a special function, prange, and that is going to execute your iterations in parallel. So some of your iterations will be done by the first core, some others will be done by the second core, etc., etc. So the work is divided for all these iterations over many cores. Well, over the cores you have available, let's put it that way. So that's very simple. You just use for I in prange rather than for I in range. Yeah, that's pretty cute. It's going to be translated under the hood to something like this. This is the C pragma or the C++ pragma in order to achieve the same thing on a standard for loop. Okay. Of course, parallelization, if I'm parallelizing a for loop, it means that all iterations must be independent. Because otherwise, this is clearly not going to work. Okay. So essentially, that has a number of restrictions. One of them is don't use Python objects in the loop body. Because otherwise the GIL is going to tell you you can't do this. And your code is going to be serial anyway. Iterations must be independent. I already mentioned it. And there should not be a break in the loop. What's the idea? Basically, you need, well, the compiler, the runtime, needs to know exactly how many iterations there are going to be. If I have a conditional break, compiler doesn't, the runtime doesn't know. And that's something that you can't do in OpenMP. Okay, so that's very easy. And here's an example for the Julia set. So basically, I'm using prange here, and I'm using a context manager with no GIL. So this actually says in the part of the code, in this context, the GIL is not active. Okay, so basically this is what you get. And this loop will be done in parallel, for loop, So basically, many points in my domain will be computed at the same time. So essentially, as many as I have cores in my machine. Okay, so what does that give you by way of parallelization? So note this is logarithmic, and this is linear. So the axes are a bit weird. So basically, if I have a single core, it takes close to 1.6 seconds. If I do that with, in this case, 16 cores, I get 0.1 second approximately, give or take, something like that. So basically, you can compute the parallel efficiency easily, and most likely, I've got the numbers here. So in pure Python, this would take, well, almost 40 minutes. Here it takes just 1.6 seconds using cycling, so it's a huge speed up. And the parallel, this is the speed up. So basically, the green line would be ideal. The blue line is what I get. So I would hope that if I use 16 cores, that my code runs 16 times faster. That's what you hope. That's really not the case. For 16 cores, I get only a speed up of approximately, okay, 11, I think, something like that. The number is probably here somewhere. So basically, I can better use the parallel efficiency. And as you can see, for 16, that drops to approximately 80%. So that means that during the execution time, 20% of the time is not spent on computation, but on waiting, essentially. Is this bad? Well, it's not that bad. 80% is reasonable, but note, this is a small number of cores. This is just 16 cores. This was done on my laptop. If you do that on an HPC system that has 96 cores, things get much more interesting. And your efficiency is going to be way less. So when you parallelize, do this type of analysis and see what efficiency at the end of the day you are getting. So how to compute them is here. These are the definitions. So that's all quite simple. You just run your code with one thread. You run it with 2 threads. You run it with 3 threads. No, okay, 3 threads, 4 threads, whatever. You measure the execution time. You can easily compute that and efficiency. If your efficiency starts dropping dramatically, it's time to stop. Either you improve parallelization, sometimes you can, sometimes you can't, or you just limit execution to a reasonable number of threads so that your parallel efficiency is still acceptable. Let's put it that way. Okay. Right. So in this case, likely, because this is actually less than 70% if I look carefully at the plot. So I would not run this application with 16 threads. I'll probably run it with at most 8 threads. Okay, now there is a good reason for this number. Why is it so much worse for 16 threads? Well, I said I did this on my laptop. And indeed, if I look, my laptop will report, or Windows will report that I've got 16 cores, but it's lying a little bit. It doesn't have 16 cores. It has actually only 8 cores and hyperthreading times 2. So that gives 16, but there are actually only 18 physical cores. So that's why if I try to use 16 cores, I don't get the best performance. So that's something that you typically see on laptops. Hyperthreading is enabled. On HPC systems, hyperthreading is not enabled. So that means if an HPC node says I've got 96 cores, it has 96 physical cores, no hyperthreading. AMD has something similar. I don't recall what it's called. I should know, but I forgot. But basically on HPC systems, you don't have to worry about this. On laptops, desktops, and so on, it will be enabled. With good reasons, but that's something else. So one of the reasons why this is not so parallelizing that well is load imbalance. Because for the Julia set, you will remember it's an iterative thing. But the number of iterations which need to be computed depend on the norm of the complex number. So there are some numbers for which you do very few iterations, and some for which you do the maximum number of iterations. So if I just naively divide my domain, my problem space, into some regular pattern, there will be some threads that just have less work to do, and some that have more work to do. So basically that means when the work that was easy is done, those threads are just sitting there, waiting until their colleagues that have a more difficult task are finally finished. So that's the problem of load balancing. And that's something that you have control over in a couple of ways. The easiest way is by specifying the schedule. So basically, typically by default, but the OpenMP standard doesn't say so, but typically in practice, it will be static. And that means that each thread just gets the same amount of work. You just divide the total number of iterations by the number of threads. The first thread gets that fraction, the second thread gets the next fraction, etc. So easy. That's static. And usually that's default. Again, no one guarantees that, but if you do something a bit more interesting, you can say, okay, I'm going to let a thread do an iteration, and as soon as it is done, it gets new work. So that's much more dynamic, because then, of course, if a thread is finished early, it just gets new work, a next iteration to do, and so on. But of course, that's much more bookkeeping. So there's overhead involved. So it's not necessarily the case that if you have a mild case of load imbalance, that just switching to dynamic is going to help you, because the load imbalance must be offset with respect to the overhead for dynamic scheduling. Much more bookkeeping, more overhead, easy. Okay. There is a chunk size. So what I can say is that I don't give a single iteration to a thread. I give a few consecutive iterations, 5, 10, whatever, to a thread. As soon as it's done with that, it gets the next chunk of 5 or 10 iterations. So basically that reduces that overhead, because less calls to the scheduler need to be made to get new work. But of course, that also potentially reduces the load balancing effect. So that is a trade-off, and that depends on the nature of the problem you're computing. Okay, you also have a schedule which is called guided, and that's similar to dynamic, but the chunk sizes increase exponentially over time. So the first chunk size each thread gets is pretty large. When it's done, it gets a next chunk size, but that's smaller. And the next will be smaller again, etc., etc. So basically, if you picture this mentally, you see that it's much easier to fill gaps with small pieces, and that should load balance better, and also reduce overhead, because you have first large chunks, so that's less overhead, and then you improve load balancing by making the chunks smaller and smaller. So that's guided. And then you can do that by using OMP set schedule, or you can do that in an environment variable as well. If you do that in an environment variable, it's of course for the whole application, and it's not necessarily the case that each iteration benefits from the same schedule. So it's better to do it fine-grained in your code using OMP set schedule. Of course, this is just a small part of a training on OpenMP, but you can do these kind of things in Cython. That's why I mentioned it. So that's a very cheap way, cheap in the sense of development effort, in order to parallelize your code. We will see other means as well. So basically, it will actually support reductions as well. So essentially, if you look at this list, something weird happens because I have a total sum here that is updated. And one of the things I said about parallelization of a for loop was all the iterations must be independent. Yeah, but this is not independent because each iteration modifies the same total sum variable. So these are not independent loops. Okay, but this is a special case. So the Cython compiler is able to recognize this as a reduction. And rather than just generating an OMP pragma, so an OpenMP pragma parallel 4, it will do a parallel 4 reduce and add some additional directive, well, an additional clause to that directive in order to make sure that total sum is a reduction variable. And then the compiler under the hood will generate some special code in order to ensure that the threads update that total sum variable appropriately without generating a race condition. Okay, so that's nice, it's automatic. If you do OpenMP, you have to do this by hand. You have to recognize that you have a reduction and you should add that clause manually. Okay. X, by the way, is automatic thread private, so you don't have to specify these kind of things again. The compiler infers that. Okay, so if you want OpenMP, you need to adapt your build file a little bit. So basically, you have to add extra compile arguments and extra link arguments. Simple, just add -f OpenMP, you're done. So quite easy, but it's a step you need to take. If you forget, that's nice, but then your P range is just going to be an ordinary range, so no parallelization is done unless you add these flags. So don't forget that. Okay. File types and imports, a bit boring. So basically, implementation files go into clicks. And declaration files are .pxd. So basically, why do you want that? Basically, you want that if you really want C access. So if you want to use C functions from within Cython. Okay, I'm not going into details. Not because it's not important, but simply because of time limitations. Why is it important? Well, I can give you an example of a Python library that uses Cython very efficiently. And that's MPI for Pi. So that's a library that's completely, well, it's a C library at the end of the day, but the wrapper for it in Python is totally done in Cython. And this type of thing is what you need in order to get that done. So you have a lot of C function calls which are wrapped in CDEF functions. If you want to do that, this is why you need this. And again, the reason why the MPI for Pi people chose to do that is performance, because it's one of the most efficient ways to get wrapper code around C functions. There are other means to do this. We'll talk about them as well, but Cython is one of the ways and one of the most efficient ways. Not the most convenient ways, that's why I'm not going into details here. So basically, this is a little bit of what that would look like, but I'm not going into the details. Okay, so conclusions. At the basic level, it's quite simple to use, and you get quite performance boost. So that's a good thing. Of course, you get parallelization sort of for free, and it's reasonable. So you saw that the parallel efficiency of my Julia code was not that brilliant, but okay, if you do that straight in C++ or in Fortran, it's also not going to be great. You always have this problem with load imbalance, so in that respect, it's quite good. I mean, it's quite impressive what happens. Okay, the problem is you need, of course, to understand Python quite well, but also you need a level of understanding at a not really trivial level of both C and C++, because you need to know what pointers are, you need to know what dynamic memory management is, if you want to exploit these features, of course. So yeah, that's a bit of a drawback. And one of the drawbacks is also that if you want to write wrapper code for C files, for C libraries, if you use Cython, it's Cython only. If tomorrow you say, well, okay, I've had it with Cython, I want to switch to Julia, your wrapper code will have to be written again. So that's a drawback. And I'm just citing Julia, it could be whatever. But basically you see where I'm going. So this effort of writing wrapper files around C libraries, Fortran libraries, whatever, is going to be Python only. And there are alternatives that don't confine you to Python. That's another reason why I'm not going into the details of Cython for wrapping C libraries. Okay, so there are quite a number of features which are not covered. So wrapping C and C++ code I didn't cover. The advantage of doing that in Cython is, as I mentioned, low overhead, especially compared to Swig. The downside is that there's quite some code to write manually. There are frameworks which do much more automatically for you, and hence that's what I would suggest as a first approach rather than doing that in Cython. Okay, so there is a Cython website, documentation, and there is also a book which I hope meanwhile got an upgrade because, of course, it was published in 2015, so it only has old-style Cython code, not a new Python type-hint type of style of coding. So that's a bit of a drawback. I would have to check whether it is a new edition. Okay, any questions about Cython? All right. Question to you, and of course to the people online. Basically, do you want to wrap C, C++, or Fortran code to use that in Python? Are you planning to do that? Or are you saying, okay, maybe I want to do that if you convince me that that's a good idea? Or that you say, well, I'm never going to do that because I don't know any of those languages and I don't care. Because it depends a little bit on how much time I spent. Well, how much time I spent on this depends on your answer. Let me perhaps first give a bit of motivation, because that might help you decide whether it's worth your while. So we already know that Python is slow. We have two ways of speeding it up. Well, three ways of speeding it up using libraries such as NumPy and so on, whatever is in the ecosystem, which is great and zero effort. We can get a speed up using NumPy. We can get a slightly better speed up using Cython. So, okay, isn't that enough? Well, it depends. It might be that you really like a certain C library, C++ library, Fortran library, for which there is no Python equivalent or no performant Python equivalent. That's one motivation to write wrappers around an existing library. Okay, but take it the other way around. What you could also do is say, well, okay, given that I can write C++ or Fortran, I can simply implement the heavy lifting. So basically the computational core of my problem, I can implement that in C++ or Fortran, but the whole scaffolding around it, file I/O, dealing with command line arguments, experimenting, etc., etc., I don't want to do in those languages because it's boring, it's annoying, and Python gives me much more flexibility. So I want high performance primitives written in a high performance language such as C, C++, or Fortran, but I want to use them as building blocks in a very flexible Python program. So that is another motivation. Okay, so now you know the motivation. So the question remains, do you want to do that or not? There is one person online who definitely says yes, and both Fortran and C++. Already been wrapping C++ code in Julia? Yeah. Okay. Yeah, how and if it can ever be done, and whether you want to consider it. Okay, let me set up a poll in order to make this a bit more quantitative, and save you typing. Where's my poll? Here. Okay. And in this case, it would be just yes, no. No, let's not do that. Let me do multiple choice. Okay. Which language or none? So never going to do this. C++ or Fortran. Well, okay, C, Fortran. And I realized that, so the C++ thing, the Fortran thing, and so on, I'm not going to do a majority thing here. The only thing is if there is, for instance, zero interest for Fortran, I'm not going to mention it. So one Fortran vote counts as I'm going to talk about it. Okay, so that should be it, I think. Oh no, I forgot. Yeah, I have Fortran. Okay, good. All right. So let's vote. How is it in the room? Meanwhile, online votes for you? Never ever. Never ever. Never ever. Never ever. Fortran, maybe? Or definitely? Okay, if it's reasonable, you do it. If it's exotic, you pass on it. Okay. All right. Sounds good. Okay, so many people for C++ and some for Fortran. It's interesting because indeed in the room almost no one is interested. Almost no one is going to do that. But online apparently interest is much larger. So I'm afraid that the people in the room have two options. Either they suffer through it or they go for an early lunch. It's up to you. Okay, so what I don't see is C, which is good because that means I'm going to skip the C part. Okay, so let's stop this thing because I know what I need to know. And let me continue with the presentation. Okay, so I already gave you the motivation, whatever. So I will give you an overview of the options because there are quite a number. And it's interesting to at least know what's out there. I'm not going to talk about all of them clearly. So there is C types that's in the standard C in the standard Python library. There are slides about it. I'm going to skip this because this is really C, not C++. Majority of you is interested in C++, so it just doesn't make sense to talk about C types. Just remember it's there. It's very useful, it's very fast. So it's definitely good, but not for you. Swig is interesting because it supports both C and C++. And the nice thing is, you only write one wrapper, and code can be generated to wrap in Python in different programming languages. So that's actually quite cute. You only do the effort once, and you have bindings for potentially many programming languages. So I'll briefly discuss this. There is PyBind 11, and that's something that I would definitely use if I wanted to bind C++ code. That would be my go-to. So I'll also talk about that. For Fortran, there is not much choice. That's just F2Py. And basically, that is very easy. So we will be done with that quite rapidly. Then there is Boost. Boost is interesting because it's two ways. I can have a C++ program that calls Python, or I can call C++ library functions from Boost. It's a bit more involved than PyBind 11, so I'm not going to discuss this, but no, if you notice two-way thing, that might be an interesting approach. Okay, so C types very fast. No, we don't care. If you're interested, just have a look at the slides. Okay, so Swig, just to give you an idea. I'm just going pretty fast over this, just to give you an idea of how it works. All right, so what have we got? We have a class, and this is just a C++ class. Okay, and I've got my header file. So this is the usual thing. Nothing special happens here. Okay, what I need to do in order to wrap this, to generate wrapper code for C++, I need to create an interface file. So that is specific to Swig. So basically, I define a module. That module will be based on the header file, so the C++ header file, and it will also include that. So basically, this is my interface file. Okay. Then I can generate two things, the C++ code for the wrapper and the Python wrapper for that C++ library which is going to be generated. That's very easy. I just take the interface file, I call Swig, I say which interface language I want, in this case Python, and the source language is C++. So it can be either C or C++. And the language I generate wrappers for can be Python, can be several others. Check the Swig documentation for the current list. So that is quite easy. So that is not so much work. What is that going to do? It's going to create a C++ file with wrapper code, and it's going to create a Python module. The Python module is magically going to ensure that when you import it, that actually the underlying C++ static object, so the shared object, rather, the dynamic library is going to be loaded. Okay, so I create now my shared library. Basically, a few important options. Set fpic, because otherwise your program pointers are off. It's a shared object, so I'm going to create a .so, and it's based on point.cxx, so my actual implementation, and the wrapper code generated based on the interface file. And I want this to go into point.so. Notice the underscore, that's a Swig thing, so don't forget to add that. Okay, then don't forget to add the wrapper file, because otherwise, yeah, you don't have a wrapper. That's pretty straightforward. Okay, and then once this shared object exists, so this dynamic library exists, I can just import the point class from the point module, and just use it as if it were a Python object. So I would say pretty neat. No glue code to write, just an interface definition, and that's it. You can, of course, wrap this into a makefile to ensure that each time you touch your C++ code, that the interface file, that the swig is called and the interface file is updated. Sorry, not the interface file is updated, but that your wrapper file is updated, etc. Let's not go there. So how do you deal with arrays? Well, quite simply. So I have my header file, and in this case, as you can see, I pass in a classic C array, so an old style array in terms of C++. And basically, in the interface file, I include carray.i. So that's an interface file that predefines stuff for arrays. Okay. And I define an array class, so double float array in this case, and that will actually generate a function, float array, which will create an object that wraps an array of doubles. So basically, my data here is created using this float array constructor, size n. So this is my data. It behaves perfectly like any Python array / Python list, however you want to call that, and I can simply call it in this wrapped function. So basically, it's very easy to also include your classic arrays in a swig interface file. So it's interesting. You have to create this interface file, which you don't have to do with C type, but of course it will happily deal with C++. And the nice thing is that basically it will allow you to generate glue code for different programming languages. Okay. So many C++ features are supported, not all of them. All right, so this can be useful. Why don't we stop here? Basically performance. So the interfaces generated by Swig are not the fastest one around. So if I'm using C++ and I want performance, I'd not necessarily use Swig. I would use Swig as a first attempt. If it's fast enough, fine. If I need better performance, I'd better use PyBind 11. So basically, again, I've got my header file, and I've got some implementation file. Sorry, this is my header file. There is an implementation file somewhere. So somewhere this add and this division function are defined. So then I need to write this C++ file that defines, there's a typo here, it's 107. Basically, I need to define the binding. So from PyBind, I include the PyBind 11 header. Okay. I also include my own header file. So basically for the classes, the functions, whatever that I want to bind. And then I define the binding using essentially macros. So this PyBind macro is going to create a module, computations, and that's the name of the module. This is the object, the C++ object that is representing that module. And then you enrich that module with several things. So for instance, I add documentation to the module. So this string here is going to be the module documentation. And of course, I can make that as verbose as I want. I can put any string there as long as I want, as informative as I want. And then I define functions with def. So this is the name of the function. And I pass in the address of the functions as they exist in the C++ library. So this is just function pointers being added. And then the rest of this is of course again help for that particular function. And for diff, I'm going to define something about the argument. So basically I'm saying that I have a Python argument, left operand, and a Python argument, right operand. So essentially that means I can call this in Python by keyword. And these are the names of those keyword parameters in the function call. A bit silly, but okay, it's just an example. Okay. Yeah, well, then basically how do I build this? Essentially, here's a CMake file. No, it's a make file, sorry. To do that, I also need to correct something here. So that's 8. I have a build file to do that. So essentially, stuff happens. I'm computing, here I'm defining the library, and the wrapper function is defined, etc., etc. So basically, it's just a simple recipe to follow. Let's not go there. This is a convenience thing. Essentially, this is just to make sure that the PyBind also links to the right Python library. So that's the magic which happens here. Okay, and the result is indeed a shared object. That's the linking flags here. All right. So it's Python version dependent. If I build this extension for Python 11, I have to redo it for Python 3.12. So basically, that's something to keep in mind. Okay, so you can also do classes. So this would be an example of a class in C++. We have 2 constructors, so it's overloaded. We have some overloaded methods just to make things a bit more interesting. So this would be the binding. Again, we include the PyBind header and so on. We create a module, in this case called stats. We add documentation. We have a Python class, statistics. So that's defined here. And then we define the Python init function, and that of course maps to the constructors. There were 2, so we have 2 of these. One no arguments, the other has a string as an argument. We add some help. Then we have other definitions. So basically these are the methods which I want to wrap in my Python object when I instantiate such a member of such a class. And apart from that, it's the same thing. So basically, name is just a method, and it's just a method, and so on. So basically, these are wrappers around my object methods in my C++ class. Nothing too much exciting happens here. What I need to do is I need to specify, in this case, I specify my function signature quite explicitly. So that's the only thing. I'm not just referring to the pointer. I'm actually specifying the signature, which I have to do because I have method overloading, remember. So basically, that's how that works. Very easy. And then, of course, I can build it as well. So basically, PyBind 11 gives you a lot more options and a lot more flexibility than Swig does. That's pretty clear. I can add documentation to my module. I can add documentation at function or a class method level and so on. So that is definitely interesting. It supports overloading, which Swig does not, and you get better performance. Of course, this implies that you need some more intimate knowledge of C++ than was required for Swig. I can take a library in C++, don't knowing it that well, wrap it with Swig without any problems. If I want to do it with PyBind 11, I have to know quite a bit more. Okay, Fortran is easy. So basically, F2Py or F2Py3 comes with SciPy. So basically, if you have SciPy installed, you've got it. And let's consider some Fortran code. So in this case, it's just a function. It computes some stuff. It has an in argument and it has a result. So basically, it's a simple mathematical function. I'm unhappy because implicit none is missing. I get nervous when implicit none is missing. Let me also add that. Probably I did it because of space restrictions, but that's not the best argument to show bad practices. Anyway, how do you do that? You simply call f2pi or f2pi3 in this case, and you want to compile it. You want to go into a module named comp.py, and it's based on this particular Fortran file. Okay, so what it's going to do is similar to what Swig did, and what bind does. It's going to create a shared object. So basically, it's going to create this guy here automatically. That's all done by f2pi. So it wraps around your compile and link step as well. So a bit more convenient. And then it's very simple. You can just use that function in your Python script very easily. I'm trying to find the function. Here it is. So basically, it works. So it's very simple. Using arrays, very, very easy. So this guy, this is a module. It contains a function that takes an array A. So as you can see, assumed shape as its argument, and it's going to return S, which is probably the sum of it or something like that. So basically, this is my module. Okay. So basically, again, I just compile my my thing with f2pi3, and now I can just import this module, or this function rather, this module, sorry, and I can call some array, and lo and behold, I can just do that on a NumPy array. So f2pi knows about NumPy arrays. Well, it knows about the buffer protocol. So anything that supports the buffer protocol can be a function argument, well, a procedure argument in Fortran without having to do any specific wrapping code. So that's done all for you automatically by f2pi3. So that's really quite useful. And basically, yeah, sorry, this was with lists, and this is with NumPy arrays. So yeah, that's really cute. You can wrap that in the make file, same thing as before, nothing special happens. In this case, it's quite simple because the building, so the compiling, the linking is all done for you automatically, so it's a very simple make file. Okay, so of course, using something like this is also a way to parallelize. You just do your parallelization at the level of C++ or at the level of Fortran. Since you're not dealing with Python objects, the GIL doesn't hurt you, doesn't do anything, and you get your parallelization at that level. So that's, of course, also something quite interesting. One thing to note with Fortran, it supports some modern Fortran features, but not all. So forget anything that starts with Fortran 2008. So that is not going to be supported by f2pi, unless they recently did some interesting updates, but I'd have to verify. So be careful. Check first the manual of f2pi and see which Fortran features are supported and which are not. Okay, so to conclude wrapping, the big advantage, in my opinion, of wrapping code is that the heavy lifting can be done in long-term high-performance programming languages such as C++, C, or Fortran. So that's a long-term investment and an investment in performance. You can do parallelization there as well. And that means that you don't have a Python lock-in. If you decide to move to a different language, such as Julia, or pick your favorite, I don't care, then basically you don't have to redo your core. And you get good performance. So that is quite interesting. Risks, where are the boundaries between your computational core and Python? So you have to guard those, because otherwise your code is going to get fuzzy and it's going to be hard to maintain. So defining upfront and be vigilant that these boundaries are not crossed is quite important from a software development perspective. You have to be quite careful with type conversions. Conversion code is going to be generated for you, but is based on the quality of what you specify. So be a bit careful there. And then, of course, if you distribute this in a package, your setup.py is going to be more complicated, because, of course, you need to ensure that your Fortran, your C++ code, etc., gets compiled. So then it's going to be a bit more work in setup.py. And then, of course, cross-platform distribution is going to be more complex. So that's basically the bottom line of those two last risks which are mentioned here. Okay, so we talked a little bit about parallelization today, basically at the level of C++, Fortran. How do we do that in Python? That's for tomorrow. So I want to conclude here, unless there are any questions, and there seems to be one in the chat. No, that was just the C++ remark. Okay, are there any questions before we adjourn for the day?
Are you at some point going to cover when is it beneficial to parallelize on a CPU and when is it beneficial to rather shift into GPU? Because as far as I understand, for arithmetic calculations, like a bunch of functions and multiplications, it's better performed to root than CPU, if I'm not wrong.
So the question is, am I going to cover when to parallelize on CPU, or as an alternative, whether to port your code to GPU? Because of course there are pros and cons for both. Am I going to cover that? We can discuss this tomorrow if you like, at some level. Let's postpone the discussion until we've talked a bit more about parallelization, because there are a few concepts which are important and which with trivial Cython parallelization you don't encounter. So let's postpone that discussion a little bit. The answer is, as usual, it strongly depends. So that's why it's very hard to answer this with yes or no, or with something that always works. Because there are some things which work quite well on GPUs, and other things that are really a very bad match. So it depends on what type of computations you're doing, whether it makes sense or not to move to GPU. In general, developing for GPU is more complicated than for CPU. That's something that is true in general. Okay. If no more questions, see you tomorrow. Same time. For me, same place.